helps if I go here. Hi, I should just appear all of a sudden. People can hear me, but they can't see me. Give another second. Anybody see people seeing? Let's see, looking forward to this, thank you. Anybody see me? Yes? Are we here? Am I on? I don't see myself yet. So I'm trying to see why. There I am. Good. Okay. Good. Hopefully everybody can hear me. Give me a thumbs up if you can hear me. I'm looking at a version on YouTube right now, watching it. I see myself now. See ya? Yes, can see and hear, and good. Is my audio sound okay? Not distorted? No problems? Everybody give me a thumbs up if everything sounds good. Wonderful. We can see and hear you. And nothing sounds distorted? Nothing sounds weird? Lovely. I see a space weather person. Good. I'm glad. Thank you. Oh, my goodness. Okay. Wonderful. I'm so glad. Okay. Great. Hi. I meant to do one of these back in January, and I tell you, with the whole Millersville program taking off, boy, I'm lecturing twice a week now, if you can believe it, at Millersville University. And it's a bit of a different experience because I'm actually having to interact with people. I see them and I hear them talk. So if I seem a little, strange, it's just because I'm used to lecturing a different way. But I've been using all the course material that we've been putting together that you guys have seen on these mini courses. This is essentially the same material that I've been teaching Millersville, and I can't tell you. I'll start off right away by saying thank you so much, because all of these courses that I'm doing here on YouTube have helped me immensely when it comes to Millersville. You guys have helped me polish the material. You've helped me find out what works and what doesn't work, and I'm just so incredibly grateful. And this is going to be yet another, and my computer just froze, so I hope everything's going to be okay. I may have to refresh it here in a second if I don't see anything. But everything excuse me, let me start over. This set of material that I'm about to do now is yet again a completely new subject, and I'm looking forward to seeing how well it plays, how well we go. This is going to be the beginning of probably 2, if not a 3-part set of courses on solar radiation storms, and basically radiation storms from the sun and, as the title says, the sun and beyond. And I've already seen a couple people in the chat who have mentioned, they said, well, why is it called the invisible killer? I'll tell you, you'll see very shortly. As a matter of fact, I'm going to open up very quickly in this course with some basic examples. I'm not going to give you specific detailed examples, but I will talk about the Apollo era and how lucky we got. And then I will go into basically the solar aspect of these radiation storms, the ones that are actually born from the sun. And we'll talk a little bit about those and how many different ways they're born and what changes them, what makes some really bad and others, very easy to deal with. And then we may not get much further than that. I'm going to try to keep this down to 2 hours or so. I know these 3-hour courses, I keep getting people who groan when I do these 3-hour courses. So I'm going to try to rein myself in, reel myself in just a little bit to see if I can make it a little bit more, manageable for you all. And then also, for those VIP members who might be watching the steering committee meeting, I had kind of teased about having a steering committee meeting today. No, ain't going to happen. I'm going to be exhausted after this, and I'm sure you all will too. So we'll probably have it in about, not quite a week, but I've got the doodle poll, and there's one other time slot that looks pretty good for us. So I'll be sending out an email to you guys here, and probably in the next, maybe within the next 24 hours or so. So get ready for that. So we'll have our steering committee meeting for this month, and we will be talking about some of this stuff. So, okay. So looks like a lot of people are, yes, great to see you back. Thanks, Andy. I appreciate that. I see a question already. Can you explain in very short, or can you give us a very short explanation what this does to solar panels for us solar users? Solar panels on the ground, not a big deal, because we are pretty much protected by our atmosphere. And I won't get into the atmospheric aspect of that yet. That will be probably the next course, but you will see a little bit when I will talk a little bit about what radiation storms do to solar panels on orbit, which is a much bigger deal. And remember, solar panels, they may be, you know, they may be a luxury down here on Earth, but up there, they're kind of what helps keep those satellites functioning and keeps their batteries charged. So those are, you know, radiation storms are a big deal to health and safety of satellites. And I will talk a little bit about that today. So you'll see at least a hint of it. Okay, and oh yeah, and if you see issues with my green screen, I apologize. I will probably have to fix the green screen at some point. These are ghosts that are coming up simply because I have a little bit of sun leaking in. This will probably change as I have a window, unfortunately, and the sun is unfortunately right in a really bad spot at the moment. So if it gets to be too irritating, let me know, and I will redo my green screen. But we'll see if we can't make it work. And it might distract me too, so who knows? I got to fix that. Anyway, okay, so as we get started, let me stand. I forget which side I'm supposed to stand on. I'll stand on this side to begin with. Let me thank my VIP steering committee. You guys are what makes all of this possible. You are helping me steer the ship. And a few of you are silent members. I would really love it if you would join us actually in our discussions, but you know, I'll just keep prodding you and poking you until you actually join us. But for all of you who do contribute and all of you who do attend the meetings, they're invaluable, absolutely invaluable. And you are definitely helping us decide where this community goes and how the field of space weather broadcasting is developing. So thank you. And then on this side, here's all my mini course patrons. I hope you can see it through all that hash on the green screen. You guys are the reasons why these courses exist, and you are training meteorologists. All this hard work that you have put in, it's not just to educate you. You are actually helping train the meteorologists right now that I'm teaching at Millersville University. And several of these people are actually in the industry. Most of them are students who are going to be out in the industry very soon. And hopefully very soon they'll be getting TV gigs, and they will have space weather chops to be able to actually talk intelligently about solar storms and solar radiation storms and things like that, as well as be able to give the first responders a heads up when inclement space weather comes, especially during natural disasters and things like that. So we are absolutely changing the paradigm of what weather is, and I can't help but thank you all enough for doing what you do. Okay, so just wanted to let you know. And let's start with no further ado. Let's begin by just reviewing very, very quickly the 4 basic types of solar phenomena that affect Earth. Right, and I'm standing in front of one of them. I forget which way I have to stand. I still do this because my green screen is mirrored. So we have solar flares. Okay, and later on you'll see a movie of a solar flare, but here's one caught in the action. This is a generator of solar radiation storms, just so you know, and we will go into that. On the other side, we have solar storms. These are also called coronal mass ejections. Okay, you can see one coming out of the sun right here, and I will show a movie of this later as well. This is on this right-hand side, you see the sun, and you see that big loop coming out. And then on the left, you see a coronagraph image, and the sun is kind of sitting here in the middle right there. And the thing is that you'll see this thing when I show you the movie. You'll see this big loop come out in white light, and it's gorgeous, and it just comes out and gets massive as it travels to Earth. Both the solar flare behind me and the solar storm, they drive radiation storms, believe it or not. And that's what we have down here. As a matter of fact, I'll play this movie. I will play right now, so you can see it. So here is what a coronagraph view at Soho, this is LASCO on Soho, sees of the solar wind. Now the sun is in the very middle. It's occulted, so we're creating a false eclipse, and all those little blast waves you see coming out, those are solar storms. Those are CMEs coming out. Okay, and if you can review the CME set of courses that I've done, and when you start seeing the snow, we call them blizzards. Here's why. Bam! Do you see that? That's a solar, bam, there's another one. That's a solar radiation storm, okay? Those actually are launched, and I'll stop it for a second. Those are actually launched when you have a solar flare and a solar storm, because oftentimes these two phenomena that I'm standing next to, they happen together. Now they're not the same phenomena, but they happen together. And if you haven't seen the courses on these two different topics, please go back into my mini courses and take a look, because we've done some very detailed work on what these two different things are, how they differ, and what generates them, and what damage they can do. But now that we've gotten the background on these two things, we can now kind of collapse them together to show how they both contribute to radiation storms, at least from the sun. And what you're seeing when you see that blizzard, and I don't know if I can go back to it. I'll try to, or maybe there'll be another one. Hold on, see if I can, there, I'll stop it at that blizzard right there. What happens when you're seeing this is, what you're seeing is actual particles from the sun being shot into the camera. Now this is a digital camera, just like, I think, yeah, this is a digital camera. I'm trying to remember, Soho was launched so long ago. Was it a CCD or not? I believe it was. This is a digital camera, and what happens is that the particles actually penetrate, right, because they're so energetic, they can actually penetrate right through the metal, right through the electronics, into the optics, into the actual digital sensor itself. And as they penetrate and most of the time pass through, what happens is that they deposit energy, and that energy is looked at as is detected as a signal. And so the detector says, oh, white, exposure. It locks it as that. You know what else does this? This exact same thing? Your eyes. Astronauts, when solar radiation storms occur, astronauts close their eyes and they see fireworks. They absolutely do. Even when they dive under the bulkheads in the ISS and they get under the big water containers, because that's one of the best protection, well, that is the best protection they can get in the ISS, they still see fireworks in their eyes. Now, they see it all the time anyway, a little bit here and there from cosmic rays. But when there's a big solar radiation storm happening, the intensity, the fluxes, the amount of particles that are coming at them are so much higher. And that's why these coronagraphs get blizzards like this. They absolutely can get blinded. Now, let's hope astronauts never get blinded by these types of things. But this is one of the reasons why you'd never do an EVA with astronauts outside of the ISS during a radiation storm. Not only are they not protected, but could you imagine? Could you imagine trying to do work and then suddenly get blinded like this? I would think it would be very frightening. Anyway, so we will talk about that. And if you notice all of these little streaks, it's because these particles are coming from all sorts of different angles. And we'll talk about that, how it looks like it's just kind of like this I want to say omnidirectional, this like just particles are coming from every single angle. It's not really like that, but once you get inside the Earth's magnetic shield, it can be like that because of the way particles move. But we will talk, believe it or not, there is a rhyme and reason to how these particles penetrate and how they move and travel, and we will talk about that. And it makes for very, very big differences in the kinds of radiation storms you see, whether one will last for a long time, whether one ramps up slowly or it peaks really fast, how it dies down, all sorts of things. So we will go into that. And then the last thing, the other type of phenomena you see is fast wind from coronal holes. This is more about the solar wind, and yes, it can drive radiation storms, not very strong ones, but it can drive radiation storms simply because oftentimes there's a shock wave in front. And it's really the shock wave of these coronal mass ejections that can really amplify and intensify these radiation storms. So anything that drives a shock wave can conceivably drive a radiation storm, and that's why these things do too. It's just not as common because they don't have what we call a seed population. You need the seed population from the flare, typically. So to get started, let's, hang on. Yeah, whoops. Why am I getting a phone call? Hold on. Let me just make sure it's nobody. Uh-oh. Hi, Jerry.
Hi, Tamitha.
Is there something wrong with my feed?
They're complaining that your audio is really low.
Oh, it's really low. Okay, cool. Thank you. Let me turn it up. Thanks, Jerry. I appreciate it. Okay, bye. Yay, my VIPs. I love you guys. You guys are just so wonderful. Let me see if I can turn my audio up a little bit. Check, 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 check. Check, check, check. Hang on. Let me turn this up here and here. Check, check, check. Check, check. Up, 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 up. Is that too loud now? Let me listen to my check, check, check. Whoa, that's really hot. Check, check. You guys sure that's not too hot? Check, check, check. How does that sound? Does that sound better, guys? Does anybody, thank you, Jerry, yeah. Anybody, this is, yeah, my VIPs are also my tech help because I have nobody to man the machine. It's just me here in the studio. So if something's wrong, you know, I have asked my VIPs, whoever happens to be watching, to help me out. So Jerry is one of my most prized possessions. I'm sorry, Jerry, I don't mean to call you a possession. My fault. That sounded terrible, didn't it? But you were one of my most esteemed colleagues, so I appreciate that. Up a little bit more. Hello, Tamitha in chat. Sounds good. I can turn mine down. Yes, ma'am. Good. Sounds good. Okay, that's better. Had to turn volume way high. Sorry about that, guys. I had no idea. It was, yeah, some people say it was okay before. It sounded okay before. What I worry about is that if it gets too hot, if the audio, the source gets too hot, it will overrun the either the preamps in the camera, or it will overrun my sling box, my sling studio, and it will distort. So everybody needs a Jerry. Yeah, I agree. I know. I need to clone him. So anybody hear any distortion? Please, if you say distortion, you know, if yes, you're hearing distortion and it's bad, tell, you know, put it in caps or something. Put distortion and I will find it. Any higher will distort. Okay, please continue. All right, so just I'll be watching the feed to see if you guys say when you went higher there was distortion and static. Hopefully, well, I turned it back just a little bit. So, all right, let's see if we can continue with this. If you see distortion from me, just let me know and we'll fix it again. So what I wanted to do is talk a little bit, just a tiny bit, about a plasma. And it's important. Okay, good, I'm still watching. Good, no distortion. I want to talk a little bit about the differences between, you know, basically the three states of matter that everybody knows: solid, liquid, and gas, and then the plasma. The reason why I'm talking about plasma is because I need to remind you what a plasma is and why, because you'll see it's very important here in just a second. So if I stand this way, here's solid, here's an example, ice, right? And it's a lattice structure. I'm not going to go over this in any detail. Here's liquid, water, right? We all know what water is. And the nice thing about water is that it's not a rigid structure, but it's still, the particles are still really close together. Then when you go to a gas, of course, gas is, you know, like a cloud, in this case water vapor, and it can fill up any container. It doesn't, gravity has a hard time playing with it. So now the particles are really free to move all over the place. And a plasma, if I stand on this side now, a plasma essentially is a gas. Okay, you can look at it in the same sense as a gas, but it's not neutral. Instead of being neutral, it's ionized. So in other words, what's happened is that you've taken the actual atoms and or molecules, and you've ripped them apart. So you have a positive and a negative charge, one or the other. Nothing's neutral. Nothing has a zero charge. There's a positive and negative charge depending upon whether you're looking at electrons or protons or whatever it is you're looking at. But these particles in a plasma, now because they're charged, they still kind of act like a gas, but now they see electric and magnetic fields, whereas before they didn't. They didn't care, right? You could just, you know, something could be magnetized. You put a magnet next to a particle that's neutral and it just drives on by, doesn't care. You put a particle next to a magnet or a particle that's driving that's charged, and there you put a magnet next to it, and depending upon what charge that particle is, it'll either steer into that magnet or it'll steer away from that magnet, depending. And it, you know, the positive or negative makes a difference. It'll either turn left or right. And that's a big deal. That's one of the reasons why when you see lightning, for example, you see these really streaks that kind of bend and crack and move and stuff like that. That's the electric and magnetic fields that are guiding them, okay? Now, the difference with space, the difference between space plasma as opposed to a plasma, you know, here at Earth, or even in the core of the sun, is that in space plasmas, they're mainly collisionless, okay? So this means the particles don't touch each other. It's a lot more vacuous. So instead of having a bunch of particles like you saw here, right, there's not so many in a collisionless plasma. So really, when you think about it, how the particles actually interact with one another, because they still do, they interact with each other only through electric and magnetic fields. So what happens is that if you can imagine something like a spider web connecting all of these little particles together, if you look at it from that point of view, and if you then you can kind of think in your mind as if you touch the magnetic field, touch the spider web over here and shake it over here, this part over here wiggles because they're all connected. But the particles never touched each other. But this is how the particles can actually communicate with one another and actually feel each other, so to speak, without really even touching. And in a nice collisionless plasma, you don't get lightning. You don't get the jagged, you get aurora-looking structures, smooth. They're very fluid and flowing and pretty, and they undulate and move because they're talking to each other, but all the movement is much more like a ballet as opposed to a billiard ball, bang, 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 bang. Do you see how that works? So, and I know there's people that have done experiments and they say, look how this changes. Well, that's why it changes. When you light up a plasma and you start sucking out most of that plasma, you get, instead of very crackly kind of looking lightning inside, you start getting this very smooth river flowing stuff that looks more like a river of light as opposed to a crackling, jagged lightning bolt. And that's why. It's all because it's collisionless. So imagine this kind of plasma and the particles around it, okay, where you've got electric and magnetic fields streaming out all the time, and then you've got these particles that have to obey what the magnetic and electric fields are saying, but they don't touch each other. So you're not going to get any bouncing off. You're going to get fluid, smooth motion. And if you keep that in mind, you'll have a better idea of where we're going next. So out in space, the other thing that you need to really pay attention to, and let me stand on this side, okay, yeah, this is good sound effects, okay, good. The next thing you need to pay attention to is something called the Parker spiral. Now, everybody probably knows the Parker Solar Probe, right? Right. Eugene Parker is the gentleman who came up with the theory of the Parker spiral in the solar wind. It's basically an Archimedean spiral. If we look down, if this is the sun here in the middle, okay, and we're looking down at the North Pole, let's say, of the sun rotates, so it's spinning, okay? Now someone's texting me. Oh boy, what's wrong? A little distortion. Okay, I'm hearing. See, you guys are keeping me honest. This is good. Let me turn this down just a smidge. Hold on. I'll turn this down. Yeah, if I get excited, my volume goes up. So let's see. Check, check, check. Check, check, check. Hopefully I didn't turn it down too much. I'm sure you guys will let me know. A little distortion at peaks, okay, and okay, there we go. All right, where was I? Okay, so this Parker spiral. So if you realize that the sun is rotating, rotating in this direction, so it's spinning, right? If you can imagine the sun putting out, shooting out solar wind all the time in a radial direction, at every angle, and that's why you see these arrows going straight out in that blue circle. See that? That is basically the solar wind being shot out radially from the sun all the time as it's kind of exploding off its solar wind. And please ignore the whistling. That's my husband. He's whistling to the birds. But then you see this interesting spiral coming off as well. And that spiral actually has to do with the magnetic field, and I'll show you. That's on this side. What's happening, and here's a different picture of the sun. This is actually a very ancient picture of the sun. I wish I had a better resolution version, but I'll show you another version in just a second. But here you see, again, here's the sun, and it's showing kind of the spin direction. You're looking down at the sun from the North Pole, and it's spinning around this way, okay? And it's shooting out these little, do you see these little parcels of plasma? You see the little squares or these little rectangle things? Boop, 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 and it says 1, 2, 3, 4, 5, 6, 7. See all that? That's like shooting parcel of plasma out first, then the second parcel, then the third parcel, then the fourth parcel. But all the while the sun is rotating. So where it shoots out the first parcel, that parcel will have traveled way far out. By the time it's rotated to the second position, it's shooting out a parcel, but it's not in the same position, so it shoots a little bit further this way. and then by the time it rotates a little bit further, then the third parcel it shoots out a little bit further this way, and these parcels are still moving out. So they get further and further away as the sun continues rotating and shooting out more parcels of plasma. Does that make sense to everybody, I hope? See, I'm used to Millersville, where I actually see everybody and go, and I see people going, uh-huh, or mm-mm, I don't understand. So forgive me that I can't do that here. But so as the sun rotates, it's shooting out these parcels of plasma, and as it continues to spin, it continues to shoot out those plasma parcels, and the plasma parcels get further and further out because they're just moving out radially. They're just moving straight out. But if you had, here's the trick, is that the sun's also shooting out not just particles, these parcels of plasma, this electrified gas, right, this magnetized and electrified gas. It is also shooting out these, it's also shooting out its magnetic field. But the magnetic field is threading. It's a single coherent line, and it's threading. It's not discrete little parcels. So it's threading all of this. And so if you draw a single magnetic field line in the sun here, you can actually see it thread through all of these. And see how it starts making a spiral? Do you see that? That is how you make an Archimedean spiral from the solar wind. And hopefully that makes sense. And my computer froze, so I hope everything's okay. Looks like everything's okay. But I can't see. Oh, I hear my husband has a microwave on, so okay, that works. Sorry, our wireless internet goes out when the microwave goes on. Go figure, right? Radio waves. So, seriously, my audio is low again? Gosh, guys. Let me turn it up here. Maybe this will make it a little bit better. I'm going to turn it up on Slingbox and see if the Sling Studio. Let's see if that works. Okay, so we have this parcel of plasma that, that's moving. Each parcel of plasma is moving out, but it's threaded by a single magnetic field line. That single magnetic field line is making like an Archimedean spiral. If this diagram didn't help you, maybe this one will. This is a little bit more intense. So again, we've got the sun, right, and it's rotating here this way, or down around if I can get the location proper, okay? And we've got parcels of plasma 1, 2, 3, 4, 5, 6, 7. Okay, so it's shooting them out in succession. Pap, pap, pap. But now we're looking at all sorts of angles at the same time. See those straight lines going out? They're all at the same time shooting out plasma, right? But we've just numbered, on just a couple of them, we've numbered 1, 2, 3, 4, 5, 6, 7. And if we lace each of those together, you can see the red line, how it gets laced together? That's kind of like the spider web we were talking about. See how that almost looks like a spider web? That's what we're talking about here. So you can see how that Archimedean spiral, if I stand completely out of the way, you can see now how that Archimedean spiral is formed, but it's only about the magnetic field. The parcels of plasma are still moving out radially, but the magnetic field looks like a spiral. Okay? Now hopefully everybody gets that. And we will go into this more when I start talking about the solar wind, when I do a course on the solar wind and high-speed streams. We'll go through this a lot. So don't worry if you don't understand it completely. The reason why I want to give you the background on this is because it has a lot to do with these radiation storms. And if you don't have a fundamental idea in your mind how the magnetic field threads all of this stuff, it's going to be hard to understand how stuff works, how it spreads out. Now, one thing you do have to keep in mind, and this I'm just to expand your mind just a little bit more. So here on this side is that Archimedean spiral I showed you. But believe it or not, how tightly wound that spiral is really depends upon the speed of the solar wind, the speed of those parcels flying out. So you can imagine in this picture here, you've got the sun. We're not drawing the whole Parker spiral, but we're drawing different potential Parker spirals. And we've got the sun in the middle, you see right here. Now the first ring, now we're still looking down at the north pole of the sun, but the first ring that we're looking at, that's the orbit of Earth, okay? The second ring we're looking at, that is the orbit of Mars, okay? And then way out here you see kind of a tan sepia tone, that's the orbit of Jupiter, just giving you an idea, okay? Now look at the spiral. You see dashed lines here, dash, 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 these different lines. Believe it or not, these are the shapes that that magnetic field would make in the spiral if the solar wind were moving at different speeds. See over here, right? See the key? I don't know if you can read it, but the top one, the solid line, is 1,200 kilometers a second, then 1,000 kilometers a second, 800, 600, 400 down here. So the slower the solar wind is moving out from the sun, the tighter the spiral. Okay? And the reason for that, you can imagine if the sun is blowing out this stuff, you know, and that wasn't distortion, that was me, blowing out this stuff at the same time radially, what happens is that if it's not blowing it out very fast, the sun can rotate a lot, and the parcels of plasma haven't gotten very far away. So the sun can really tighten, you know, wind up that spiral. But if the parcels of plasma are moving out really fast, like this, then that sun doesn't get to rotate very far before that parcel's way out there. So it doesn't make much of an Archimedean spiral. It's kind of like a sprinkler. You've seen those sprinklers that spin and they let jets of water out? If you look at it, if you took a freeze frame of those sprinklers in action, you'd see they'd have an Archimedean spiral. The water lets out in a spiral. And depending upon how fast those sprinklers are spinning relative to the water coming out will mean how tight that spiral is. And it's the same thing with the sun. So you can kind of think of the sun, believe it or not, as a little spiral sprinkler sprinkling out its water to the solar system. Watering the flowers, I guess, watering life. I don't know. It's kind of silly to think of it that way, but you know, that's actually how it works. It's a very similar kind of concept. And we actually have seen this. It may seem really silly that it's actually that simple, but it is. So hopefully that that makes sense to you all. I've lost my feed. I may have to redo my feed here, and I'll do that in a few minutes. So I don't know if you have any questions, but I'll check in just a moment. So what I also want to show you here is, with the whole kind of concept of the solar wind in mind, and how the Archimedean spiral works, and that you have these big long spiral arms coming out of even our star when it comes to the magnetic field. Now we need to talk about how particles move in that. Because if the sun is shooting out these particles, well, they're going to see that magnetic field. They're going to see that spiral. And they're going to be jailed by it. I'm sure you've heard me talk about jailing. And we call it frozen in flux. And the reason for that, it's really that we talk about the magnetic field being frozen into the particles. But in actuality, oh good, okay, I'm seeing my feed's back, so I'm seeing your comments. It looks like everybody's pretty much understanding it, so good, good, good. So back to the particles. So what happens is that a magnetic field and the particles kind of are jailed together. So where the magnetic field goes, the particles go. Where the particles go, the field goes. It's the same. They're really kind of interlocked for the most part. There are times when they're not, but in this situation they are. And what happens with these particles? Remember I said if you put a magnet next to a particle that's charged, that it will move, it will bend or turn? Yes, same thing. In this case, believe it or not, the particles, you guys have seen me with slinkies more times than I can count. Believe it or not, this is the path that particles take. If I have a magnetic field that's threading this, like I'm threading the eye of the needle here, and I'm looking, let's say a line from my eye to yours is a magnetic field line. If there's particles around them, this is the path they take. They will take a slinky. They will take a helical path. They will absolutely wrap around that field, and depending upon how fast they're moving along, if the field is moving up and down, field is straight up and down, let's say, a field line, depending upon how much speed they have in this direction or this direction, that will dictate how tightly wound this helical path is. If they don't have a lot of speed, the helical path will be very tight. They'll wrap around and wrap around and wrap around and not move very much. If they're moving really fast in this direction along the magnetic field, their helical path will be very loose because they'll be wrapping around at the same time they're spiraling up and down. Now, what dictates that? Well, believe it or not, the mass of the particle is a huge one. Charge of the particle, right? Because we have to talk about things like inertia, but then we also have to talk about things like charge, because charge with magnetic fields and electric fields gives you forces. So it's really kind of an interplay between those things. But as a general rule, what we end up finding for most things in the solar wind is that particles that are heavier, bigger, like, protons, anything, you have electrons, which are really, really tiny, then you have protons, which are much larger, and then you have even larger atoms, nuclei, helium, oxygen, iron, things like that. All of that stuff comes out. Those particles, the larger they are, essentially, the wider, the bigger spiral they make. In other words, the bigger the helix they make around a field line. And so that's what I'm kind of standing in front of. Let's see if I can move off to the side and show you what I'm talking about. So here's a picture of the sun, right, a chronograph of the sun. And here, in this case, they're showing a big CME come out, but that's not a big deal. All they're just trying to show you is that shock, that white line in front of the CME, is the driver of let's say, a solar energetic particle event, which we'll get into in a second. And so we've got this arm. Let's say that this little white line this way that's going to the ACE spacecraft, that is one of the Archimedean spiral arms. Okay, let's just pretend that that's the case. And in that, we've got two different types of particles. We've got an oxygen atom, or an oxygen, ion in this case. It's charged, and that's the spiral in yellow. Okay, and it's going to spiral around. And then we've got an iron nucleus, so it's an iron, ion, and its spiral. Look how much larger its spiral is. Okay, and that matters because. And we won't go into that too much in this particular course, but I want you to keep that in mind because it matters in terms of when and where you're going to see these particles, what abundance you're going to see these particles in, and what potentially even gets there first. So you can imagine with oxygen and iron, you're going to see certain signatures, and they could probably be, and they will be very different actually. And then with other particles, smaller ones, let's say electrons. Okay, so let me show you this. Here's the sun, right here, if I can actually point to it. Okay, there's the sun. There's part of the Archimedean spiral you see. And now in these, and what I've done is that, see that spiral arm? I try to have that spiral kind of go out and match this, where you see the orbit of iron and oxygen. I'm trying to match that dashed line to that white line, which is that Archimedean spiral, to give you a better idea. And then here's a couple other examples of more slinkies. Imagine even smaller particles, like electrons. They're going to spiral even tighter, more tightly around that, around those Archimedean spirals. They're actually spiral, I think, in the opposite direction because of their charge. But their spirals are going to be tighter, and they can actually travel faster and further because they don't have nearly as much inertia. Okay, so that should give you a hint that maybe electrons and protons, because we get a lot of this stuff, we get all sorts of different species that come out with these solar energetic, these radiation storms, that some of them may come out earlier than others, and some of them may be, we could use them as maybe precursors to bigger, heavier atoms and ions that come out more slowly, right? And that is exactly what we end up doing. Now, I won't talk about that so much today, but I will give you a hint of it. So hopefully that makes sense. Again, my thing is, my chat is kind of frozen, so I hope you guys are seeing this. Okay, so let's talk about for just a moment what most people, what most educated people and astronomers look at as space radiation. They kind of just classify it mainly as three major types. And here's how it works. For example, this is a great example. They say, okay, we've got three types of space radiation. It's just, you can just call it space radiation. Don't worry about it. You've got galactic cosmic rays coming from supernova, and they cause a problem. And then you've got trapped radiation that comes from Earth's radiation belts and inside Earth's magnetic shield, and solar energetic particles. And for the most part, protons, protons, protons. It's all the same. No, it's not. First of all, it's not just all protons. we've got everything under the sun, literally. So everything in the periodic table comes at you with at least with this galactic cosmic ray radiation, and believe it or not, with solar energetic particles as well. Trapped radiation is basically that. It's trapped, and the source is typically somewhere else. So cosmic rays or energetic particles in some cases. Other cases, it's just like some of the ions from our atmosphere can get caught up in it. That come out, they kind of are escaping, and they can get caught up in it. And it's also just the proton and electron soup that we live in. And a lot of times it's the trap stuff ends up being, it doesn't even end up being all that energetic to begin with. The particles, the source of those particles, really aren't what we would consider a radiation storm. But because of the way our Earth shield works, our Earth shield ends up being like a particle accelerator. It's like a big tokamak. And believe it or not, during solar storms, it will accelerate its own. That tokamak starts working, and it starts pumping it out. And it will accelerate these particles inside the radiation belts and bring them up higher and higher and higher and higher energies. And that's a real problem for satellite operators, because we always have particles in these radiation belts. And sometimes they're kind of calm, and other times they're really inflated. And it's not because new particles come in. It's because our Earth shield is dumping energy into it's how do I say this? The environment is such that the Earth's shield gets stronger. It actually makes that Earth shield stronger. And so it ends up accelerating these particles that were once kind of, not too energetic, to sometimes really high energies. And it's not just a dumping of particles into these areas where they get trapped. It's just that you can accelerate these particles into really high energies, and then they just can't get away. They can't get out. So they have to just sit there until another big storm comes and washes the whole thing away. So trapped radiation is almost a different animal. It's got a different behavior. There's different things that are associated with it because it's not really born of our star or from other stars. So really, it's in a class by itself. And I will talk about this probably in maybe the second or third class. I won't really talk about much of it here, except to give you an idea of what damage this stuff can do, so you can get an idea of why it is even in this class. It's very important. So, and I might, in the next couple slides also, I'll be showing you a little bit more about these types of radiation, essentially what kind of basic examples, how do these types of solar radiation and cosmic radiation actually affect us. But let me try to give you an idea that it's not just those three. You can kind of collapse everything into those three areas, but there's really a whole zoo when it comes to, let me see, am I standing on the right side? Yeah, no. There's really a whole zoo when it comes to radiation in the universe or in our solar system. We've got galactic cosmic rays that come in from the outside, as well as anomalous cosmic rays. So you have what we call GCRs as well as ACRs. GCRs are typically protons, but they can be anything under the sun. Anomalous cosmic rays are the same stuff, but they're oftentimes much heavier ions, and they come from a slightly different source. I'm not going to get into that right now. Well, of course, we have solar energetic particles. They're often called SEPs. That's the science jargon. Remember, all of this stuff is the science jargon, by the way. And don't get them confused with energetic storm particles, which are ESPs. A lot of people think that these terms are interchangeable. They're not, simply because of how they're driven. Energetic storm particles, we will talk about how they contribute to SEPs, but they're not exactly the same. And then we have, I told you, the co-rotating interaction regions. That's actually the fast solar wind. And that stuff comes from bow shocks, from interplanetary shocks. And then we also have bow shocks in front of planets. Not going to go into all this. Trust me, there's not going to be a test later on it. I just wanted you to see the wide range of, basically the whole zoo of sources just locally to us, to our star, where we can actually get these different types of radiation storms. So we don't even have to go to galaxy M31 or look at outrageous things that are light, many, many, many light years away. We have plenty of sources of radiation storms just in our local environment. And believe it or not, astronauts have to deal with all this. They're a little bit protected in our shield. Of course, our shield causes problems too, as I just mentioned. But when we get out into interplanetary space, there's tons of sources of stuff. And it is continuing to be one of the biggest problems regarding interplanetary travel. And it will be for quite some time, because it's very hard to shield against them. Now, getting back to what we will be talking about, instead of that whole zoo, what we will be talking about throughout this course is going to be essentially two sources of radiation storms. Now, granted, whoops, let me stay on this side. Granted, I'm not going to be talking about, I will go into trap radiation at some point, but it's not really a source. It is, but it's not a seed population. It's a source in the sense that you take less energetic particles and you accelerate them. You give them energy and make them super. This wasn't a super particle, but now it's a super particle. It's, that's where the phrase things like killer electrons comes from. But we will talk about that as a different animal. In this case, the main two that we're going to be worrying about are galactic cosmic rays, and I'll talk about that probably in the second course, and then solar particle events. Okay? And you get, and I wanted to remind you that you get protons, neutrons, oxygen, helium, mainly, but you get iron, you can get carbon, you can get, believe it or not, you can get all the way down to some of the precious metals that we see. There are these abundances, and we call them ultra heavies, and you do see them. And thank goodness for that. Otherwise, we wouldn't have all of the wonderful diversity of the elements that we see on our planet. And a lot of it comes from these radiation storms. It's not all supernovas. Now, let's talk a little bit about how these things have affected us in the past. And sadly, I don't know. I've always been, I always have to say this with mixed emotions, because happily nobody got hurt. Sadly, we didn't learn anything. The Apollo era gave us a really great chance to understand how dangerous space is, and we missed it by that much, for any of you who are old enough to know where that reference comes from. The sad thing is, we actually had, a massive program that lasted years and years and years, right? 69 through what, 72, 74, I forget when was the last Apollo mission done. Quite a few, it was a decent sized program. And this period, believe it or not, was actually during a solar maximum. We had a solar max, I think, in either 1969 or 1970. So how in the world did we manage to send so many missions of people to the moon and not get nailed by one of these solar radiation storms? Well, to this day, people say luck, just pure luck. So we had, if you look down here at this bottom right here, if I can stand out of the way, okay. Down here at the bottom, you've got a couple pictures here that kind of show where things are, but really what I want you to look at, hopefully you can read this, is this chart down here at the bottom, and I'm going to try to see if I can read it. Okay, what you've got is a list of exposures, and it goes from, it's kind of like a stoplight chart. It goes from yellow, which is, it should be green, which is the annual exposure down here for a human on Earth. Okay, and this is a timeline going from 1968 all the way to like 1972, 73. And then in blue, right here, see these numbers? This is the Apollo mission, which Apollo mission we had, right? So there's 7, 8, 9, 10, 11, 12. I have to look at my computer to make sure I know the numbers. 7, 8, 9, 10, 11, 12, all the way up to 17. Okay, those were the Apollo missions, I believe. So we've got the natural annual exposure down here on the Earth, on the planet, and then varying levels of radiation dose as you go up. Obviously, red is fatal. I think orange is sickness. Let's see, what does it say? Short-term radiation sickness. And then the light orange, this kind of yellowish orange here, the second from the bottom, is the annual dose for a radiation worker, okay, here on Earth. And then, of course, down there is, you and me, right? So if you look where the blue lines intersect, you see Nothing. You see there was nothing happening. All of them basically, all the blue lines go all the way down basically to the bottom, right? Because that's where that marks the timeline for when those Apollo missions happened. But if you look at the lines that go up, those are the radiation storms that occurred all during that period. And if you can notice, if there had been multiple missions, if we had lined up with any of these missions, people would have gotten up easily, many times, past the annual dose for a radiation worker in one mission. They would have gotten beyond an entire year's worth of radiation for a radiation worker, not even a public servant, but a radiation worker. In some cases, we would have, even in one mission, would have gotten to the point where they had gotten sick from radiation poisoning, temporary sickness, which probably had long-term lasting effects. But in one case, between Apollo 16 and Apollo 17, see this right here? See how it goes, how that one goes way above the red line? If the Apollo 16 or Apollo 17 had occurred in 1972 during that August radiation storm, it would have killed everybody aboard. Now, this is the dose that we got out in pristine space, which is also the dose that you would get on the moon because there's no atmosphere. The radiation goes all the way down to the surface. We don't get this at Earth. Our atmosphere protects us. We get cosmic ray showers, but it penetrates only so far. And for the most part, we really don't get anything, very, very little radiation down here at the surface of the planet. Mars is a different story because Mars is has a much weaker, thinner atmosphere. So particles penetrate, radiation storms penetrate all the way to the ground. But at the moon, not only do they have penetration all the way to the ground, so anybody playing golf on the surface or in the little dune buggies would have been in trouble, but anybody in those capsules, let's say they were flying to the moon at the time, and the moon happened to be outside of our Earth's magnetic shield, let's say, which the moon does quite frequently. If you are inside one of those metal capsules, suddenly that strong a radiation storm actually, as it penetrates the metal hull of your capsule, the metal hull of the capsule itself becomes a source. And so you end up getting even a higher dose of radiation inside the capsule than you do even outside. So there's a chance that this, as fatal as it is for this one, could have been an underestimation. So they would have died potentially many times over. So am I happy? Yes, I'm thrilled. No one got hurt. We had a very, successful mission or set of missions that made space look like it was conquerable. But I'm also sad because we didn't learn anything about space weather. We didn't learn how dangerous space weather can be. I mean, granted, I would never wish one of these storms on anyone. Not a chance. But I sure wouldn't have minded one of these down here where they got like, what in the heck is this? We're getting something where it's like, oh gosh, you guys, we got to abort the mission. We got to come home. Wow, space is dangerous. We got to figure this out. That wouldn't have been bad. But we got nothing. Look how many missions we did. I mean, somebody was looking out for us, huh? But unfortunately, it's also caused us to become very cavalier. And now a lot of people think, well, the radiation problem is solved. I mean, look at Apollo, right? It's not a big deal. And if you're really crazy, then you say, well, Apollo never happened. It all happened in a soundstage. So, of course, you got lucky. I'm not of that ilk, but there are people who believe that. So, yeah, a manned mission to Mars will not go well. Right. Why do you think I'm doing this? Yeah. The part of the problem with the manned mission to Mars is that everybody's worried about, they're just simply worried about getting to Mars. They're not even worried about once they get there, how do you now deal with an atmosphere that's basically non-existent? And you plan to take, what is it, a 6-month trip, one way, and then be on, have the main mission for 2 years on the planet, or even 6 months on the planet, and then have another 6-month trip back. So now you're talking about, 18 months to 24 months, and you're going to go when Earth and Mars are the closest together because it makes the interplanetary trip short. Oh yeah, but guess what? That lines up during solar maximum. You want to go during solar maximum, really? Are you sure that's the safest time to go? And not enough people are paying attention to the fact that maybe that's not. Maybe it's better to have a longer interplanetary trip when there's a much less chance for a bunch of these radiation storms. I don't know. I don't know if anyone's ever done that trade. And there's just so many things to think about, because even low doses of cosmic rays, for example, during solar minimum, which are worse during solar minimum, that may be even more dangerous biologically than having a big, fast burst of radiation and just get sick and get over with. We don't know enough about radiation sickness and biology and how these things act to know which is worse. So yes, we're being extremely cavalier, and I hate to say it, but the first astronauts to go out and do this are going to be incredible guinea pigs, and they have no idea what they're in for. So enough of that. So let's go back to solar energetic particles. Now that I've kind of given you an idea of what they are and how they can affect humans and how we got lucky, let's just define them. Now, I took this from a heliospheric course, or a heliophysics course, I think a summer school for NASA, and I thought Dr. Yang did a good job of describing them. So energetic particles such as electrons, protons, and what we call other heavy ions are traveling much faster than ambient particles in the space plasma, so they're not just moving with the solar wind. They're actually traveling at a relativistic speeds, basically really close to the speed of light. Okay? And they can travel from the sun to the Earth in an hour or less. Okay, so this is really fast. It's not light speed, but it's close. Part of light speed. That's part of the reason why they can travel through things, through metal hulls of spacecraft. Makes it very easy for them to do, simply because they are so energetic. Okay? And yes, the term SEP usually refers to protons typically, not because it only is protons, but because, and oftentimes you'll see it, solar energetic proton or solar energetic particle. Oftentimes they mean this, you kind of look at it as the same thing. Mainly because protons are just the most abundant. Protons are everywhere. What we call the fluxes, the amount of them is so high relative to the amount of other species. They oftentimes are interchangeable. We get lazy. It's really what it comes down to with scientists. So let me see if I can stand in front of this horrible, no, stand over here. See if I can stand in front of this horrible sunlight. So why do we care? Well, these radiation storms can create all sorts of havoc, and I've already kind of gone over this, but I like this little plot, and so I wanted to just share it with you really fast. So solar energetic particles from solar flares and coronal mass ejections, as well as GCRs, and the trap radiation, that's the South Atlantic anomaly. They've kind of, in this plot, they've got to kind of drawn in some of the things that they affect. Now, spacecraft, I'll talk a little bit about that and give you a really gentle few examples. I have some specific examples I'll show later, probably in a second class. Humans in space and in air, so you can see both astronauts and at high flights over the poles, flights at high latitudes, long duration flights. This is becoming a bigger and bigger issue, where radiation storms can pose issues for them. And then, of course, also for communication and navigation. We already know everybody uses GPS and on their cell phones. If you're at high latitudes, believe it or not, radiation storms can cause a problem for you. Not because it's affecting your phone, but because it's affecting the upper atmosphere up there, and it's making the ionosphere very hard to penetrate. So the satellite signals, they're still chirping out their GPS positions to you. It's just that you can't receive it, because there's all this hash up there. Remember when we talked about the coronagraphs and you saw that static? You saw all the blizzard? Imagine kind of like a blizzard like that, because there's all these cosmic ray showers that are happening from all these particles penetrating. And I'm sorry I didn't put a picture of that. I'll talk about that next time, because when I talk about cosmic rays, you'll see cosmic ray showers, what they look like. Well, radiation storm showers are the same thing, and they happen at high altitudes, but it causes this real nasty, screen of stuff that makes it very difficult to receive GPS signals, as well as any other type of satellite signal. And it's especially critical for things like communication and navigation, because that's where you need this two-way talking, or you need, constant pinging to be able to know where you are. And that's a problem. And it's also a problem for amateur radio operators, even at lower latitudes. Now, particle radiation is just a portion of a huge set of stuff when it comes to health and safety of spacecraft. Again, I'm not going to go over that for this particular talk, but I do know a lot about all this stuff. So this is going to become more and more important as time goes on. As a matter of fact, this chart is slightly wrong because there's some things that are missing, to believe it or not. In the ultraviolet and X-ray for surface erosion, they're not showing plasma, and actually, the plasma actually affects surface erosion quite a bit. That could be an issue here. That I need to have this chart be updated. But this is all to do with essentially health and safety of spacecraft. And as we become a Starlink generation, I don't know if I should be calling us that, but as we become something like a Starlink generation, as a OneWeb generation, these types of things become a bigger and bigger issue. And pretty soon, this is going to have to be reported in weather, so that the average consumer can understand why they don't get their Sirius XM radio for the day, or their Starlink connection, or they're having issues with their GPS not connecting, or getting different solutions that then fail, and then they lose lock and get it again, and all sorts of things. Because as we get to be more of a spacefaring world, a spacefaring society, this stuff becomes critical. Another example, and here's just a couple quick examples for you. Damage to satellites. So if you wanted to look up on Google or on Wikipedia, the Telstar 401 way back in 1997, when we still had pagers. Anybody remember what a pager was? Telstar went out, and for 2 or 3 days, they called it an act of God, and it just absolutely took out the spacecraft. And it took a while for people to even realize that it was a space weather event that did it. The Galaxy 4 in 1998 cost $250 million to fix. There was a similar disruption. We get satellite damage all the time. These are just a couple of many examples. If anybody remembers in Canada the Anik satellites, Anik 1 and 2. This is a headline from Canada, from Canadian newspapers, talking about how their television satellites got knocked out simply because they weren't paying attention to space weather and didn't make sure that their satellites were capable of handling the types of radiation storms that we get. There's all sorts of things. Satellite anomalies, there's the South Atlantic anomaly, well, again, I'm not going through. A lot of this stuff has to do with the trapped radiation, but it is very relevant, and the annual losses can reach into the millions. And now that we're getting into hundreds of millions, and now that we're getting into things like Starlink and OneWeb, oh my gosh, this type of cost and these types of incidents are just going to, I hopefully not skyrocket, but it will definitely go up before it goes down. I think we're going to be a lot of lessons learned, and then people will start getting savvy, and hopefully the issues will subside as we get a little bit smarter about how we make our satellites. Other issues, orientation problems. You can imagine satellites that use star trackers, so they see stars, and they use the stars to point, like in this figure here. But remember what happened to the chronograph, the blizzard. You get something that looks like this suddenly in your star tracker, and your star tracker goes, what? What happened, right? And you haven't figured out how to mitigate that if you don't have a redundant system that can handle being blinded by radiation storms. And sometimes this degradation can be permanent, depending upon what type of optical coatings you have that can be ripped up by these radiation storms. So there's just a whole host of stuff. Now, what about at Earth? So that's some ideas on satellites in space, in the near-Earth environment. What about Earth itself? Well, ozone, anybody? Here's an example, and I've got multiple examples of this, which I won't show today, but here's one from just one of the Halloween storms. Remember those blizzards I showed you? One of those was a Halloween, well, several of them were the Halloween events. So those radiation storms did this. Believe it or not, they actually took out the ozone layer. This is NOAA 16. So this isn't, okay. So this is the NOAA 16 satellite, and it's showing the ozone layer, probably the fluxes of ozone in the layer and how much it decreased. And you can see this model over here. It reduced the content of ozone to a massive degree for 8 months. And this was at about 42 kilometers in height. So, wow. There was a Carrington, and this is just a Halloween event, so this is a superstorm, but it's not like the Carrington class events. Carrington class events, there was one in 1972, and they actually were able to measure the ozone at that time when the radiation storm hit. They got measurements, but because back then in 1972 we hardly even knew there was a solar wind. We didn't even really know what solar storms were, let alone radiation storms. So we've had to kind of rebuild the observations of what we saw using simulations and models. But from the sparse observations that we had, the simulations tell us regarding the ozone content for the 1972 Carrington class event that hit, it took 4 years for the ozone to repair itself. So anybody who thinks that radiation storms aren't a big deal, think again. They can be very, very devastating. It is not just CFCs that cause ozone holes. We have natural versions of them too. Oh, this isn't supposed to be the first one. That's supposed to be the first one. Okay. So let me stop here for just a second. I've talked for about a little over an hour. Let me see if anybody has any questions thus far before I get into some of the specifics of solar radiation storms. I also may rekey. I don't know. I'll just see if I can stand over that. That sucks. Anybody have any questions thus far about what I've gone over? So I guess you can't blame hydrocarbons. No, you can't. You cannot blame that for all the ozone depletion. It's crazy, but solar radiation storms do it too. Magnets don't stop powerful, fast-moving neutral particles. No, they don't. They also don't stop neutrons. And that's a problem too that we have to face, especially when you have atmospheres or you have bodies with no atmosphere. The neutron albedo, for example, at the moon, from the solar UV hitting the soil, the dust on the moon, there's actually a neutron. It liberates neutrons right from the soil. And that's going to be a problem, I think, for workers working asteroids, because asteroids don't have atmospheres either. So the solar radiation, just the UV radiation and the gamma rays and all this, just the normal particulate less, we're talking zero mass radiation that hits the surface of these bodies that have no atmosphere. There's going to be neutrons liberated, and neutrons go right through people. I mean, they're very dangerous type of radiation. And again, not much is known, because here on Earth, we have an atmosphere to protect us. We don't realize how hostile space can be and how hostile it's going to be going to other planets. People worry about gravity. They worry about, not having enough water. They worry about all sorts of stuff. But they don't really worry about radiation. And I don't know why. It's ridiculous, but they don't yet. Okay. Do the atoms orbit because one charge is on average closer to a region with a higher flux? Yikes. Do they occur together? I'm not sure do the atoms orbit? One charge is on average closer. I don't understand that question. Sorry. Try to rephrase that question again for me so I can understand that. That maybe simplify the question for me and ask it in multiple parts so that I can understand it. But I don't get it quite the way you've asked it. Is Earth more vulnerable with a weakening magnetic field? It is yes and no. Yeah, I've seen a lot of questions. Okay, I'm probably gonna have to miss some, so you'll have to post some again. But I'll answer the Earth's magnetic field question because that's important. I know a lot of people are worried about our field weakening. It's a little bit concerning only from the point of view of us having to probably lose a tiny bit of our atmosphere. What's happening with the Earth shield that's weakening, it's not the whole shield that's weakening. It's only one component of it. It's the strongest component, granted, but it's only one component. And what's happening is that as that dipole, we call the dipole field component, as that field component is weakening, it's flipping. It's going to pass through zero and then it's going to reemerge again, but it's going to be aligned the opposite direction magnetically. When it flips to zero, or as it's flipping to zero, it's revealing the other components. We have a whole bunch of components to our magnetic shield. The dipole field is the simplest, and then we have a quadrupole field, an octupole field, and in even higher order terms. And yes, quadrupole means 4 poles. Yes, we won't have a north and south. We'll have like a northwest, a southeast, a northeast, and we'll have all sorts of, we'll have 4 poles that are kind of maybe at mid-latitudes. That's actually what's causing the poles to migrate right now. We see the North Pole kind of moving, the poles are changing. That's because, as I've said before, I've likened it to kind of like draining a bathtub imagine you have a bunch of little toys. I have a 6-year-old, or I mean a 10-year-old, so I'm going to be using kid analogies. So imagine draining a dirty bathtub where you can't see the toys submerged under the water until the water gets down, and then you start seeing them being revealed as the water drains out. That drainage is like the dipole field draining out, and as the water continues to drain down, you start seeing the emergence of these toys, these other poles, these other components to the field. And so it's affecting where that North Pole and the South Pole is right now, because it's actually moving closer to where the quadrupole field will have its poles. In actuality, the North Pole will probably split into 2, the South Pole will split into 2, and we'll have 4 poles for a little while. And then once the dipole field reverses and starts growing again, then those 2 poles will begin to merge again and change position, and we will get back to a single North Pole and a single South Pole. It's just that the magnetic field will have reversed. So, but in the meantime, it's going to be pretty crazy. It's going to wreak some havoc. Now, is that going to make all of our atmosphere disappear? No, absolutely not. Are we going to get a thinner atmosphere? No, because we've got a lot of water. This is a water planet. So what's going to happen is that, if we need to, the oceans will just evaporate a little bit more water. We got a really nice buffer system. It's not going to be a problem. I doubt we'll even notice it. But it will just cause northern lights and southern lights to be in different places. It'll cause radiation storms to come in different areas. It's definitely going to change our near-Earth environment dramatically, because I have no idea what's going to happen to the radiation belts that we have right now. I mean, I've looked at models of the Earth's magnetic field during this transition, and it's like spaghetti. It's like taffy. I mean, the magnetic field lines are just all over the place, and it's like, gosh, are we even going to have radiation belts? Because it doesn't look like there's anything stable in there. Everything may just fly off and leave. So who knows what that's going to be like. But for us down here on the surface, I don't think it's going to be a problem at all. The biggest issue is going to be for navigation, because our field is going to be changing so much that our compasses are going to be weird. Like you'll have to buy a compass every year, because the compass won't be valid. Our field will change so much that whatever it's reading here is not going to be labeled properly. So that's going to be probably the biggest challenge for us. Outside of that, I don't think any issues as far as radiation storms on the planet are concerned. We'll be able to handle it when it happens, and that's still hundreds of years away, I think. Anyway, don't worry about it. Hopefully that answers that question. Okay. Let's see. We are going through a magnetic field reversal. Is weekend entering a new solar cycle? What could go wrong, right? We have a ways to go yet. I don't think you're going to even notice. The aurora is going to be slightly in a different place. So the pole is moving over Siberia, or getting closer to Siberia. So Siberia is going to have a little bit better aurora show than they ever used to. The Canada and the United States, which has always enjoyed really good aurora shows during big solar storms, may get a little bit less than we're used to. It's really not that huge a deal. Outside of that, we're not going to notice much of a difference easily in our lifetimes, and probably in our children's lifetimes as well. Our children might see something, but it's going to be more like our, great grandkids that'll see stuff. Okay, so yeah, don't label the compass. There we go. So who's getting their radios set up for DXing for solar cycle 25? I am. Good for you. You notice the solar flux is already coming up. Yeah, we're sitting in the low 70s, even with a spotless sun. So it's getting there, guys. It's getting there. There's even a couple bright regions on the sun right now. All right, so I am going to jump into this next little bit, and I am keeping an eye on the clock. I don't want to go too long, so we'll see how far we get, but I'm going to try to stop this by 1 o'clock at the latest. So let's talk a little bit about these solar flares and the solar storms solar radiation storms created by solar flares and solar storms. And I do believe this is where I have my movies. Yes. So we'll talk about a solar flare for those of you who do not know what a solar flare is. Here is one. I'm sorry, you got the arrow right there, but you can see it. Whoops. If I stand out of the way, let's try that again. There we go. There is a nice solar flare. That was like an X2 solar flare. And for those of you who are interested, there's not going to be a test later, so you don't have to worry about it. Actually, I'll still stand on the side. It's a lot of energy release, 10 to 32 ergs if you care, and plasma on the sun's surface can be heated to 10 megakelvin. And here's the part that really matters, is that these solar flares can accelerate a seed population up to around, for electrons, around, and maybe a little higher than 100 MeV for those people who care. 100 MeV is very, very energetic, much higher than you'd ever get in the Earth's radiation belts, for example. So trap radiation doesn't get this energetic, at least in the outer zone. And ions can be energized up to 1 GeV, so that's even higher than MeV, and that tells you a lot. For those of you who are interested in the science jargon, magnetic energy, of course, is being released in the solar corona. There's slow shocks. There's the solar flare mechanism, and I'll kind of remind you what that looks like in a little bit. But if you really want to see what the standard flare model is, you need to go back to my mini courses on solar flares, and you'll see probably far more information about that than you really want to. It goes into solar flares and radio bursts, but that same mechanism that generates radio bursts also and generates a lot of the really energetic light that you see also accelerates particles. So it can not just accelerate waves and stuff, it also accelerates particle beams, and some of those generate those solar radio bursts. So it all goes kind of hand in hand. That's the thing with these space weather phenomena. They all are different, but they all happen at the same time, and that's what part and parcel why things are so confusing. Now, if I go to the solar storm side of things, now remember, before I go, solar flares, these things happen in 8 minutes. The light reaches us. They're here and they're gone. The radio bursts that happen travel at the speed of light. Everything travels very, very fast. So it's here and it's gone, okay? When you get the solar radio bursts, it's up for about an hour, maybe a couple hours, and then it quiets down. That's solar flares, and that creates a seed population of solar energetic particles. And you can imagine, as you'll see shortly, if it's just solar flare generated, the solar energetic particles kind of follow the same kind of behavior as the flare does. It's here and then it's gone really quickly, okay? But there's a totally different animal. Radiation or solar storms, so CMEs. Now let me show you a CME. Whoops. Oh, come on. Didn't you play? Why can't you play? There it is. Wonder why it did that to me. Okay. So here is, on this side, you see that loop come out. Boom, right there. I froze it so that you could see. That's part of that jailing mechanism where the magnetic field is jailing all that plasma. So on this side, you see the sun and this big loop coming out. On this far side, you see a coronagraph view. You see the sun in the middle, and then here comes out that loop. It's that same loop. You can see it coming out through the coronagraphs, and this takes it out to 15 sun lengths. Look how big that thing is. Now I'm going to stop it right here, if I can. Stop. Ugh, crazy thing. Why is it? Isn't that weird? There we go. I wonder why it doesn't let me do that. Let me let this play again, and I'm going to keep myself right here so I can stop it as soon as it comes. Oh no. There we go. I have to keep this thing moving. La da 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 da. Come on, don't go away. The reason why I'm doing it, believe it or not, there is a method to my madness here. I don't want this thing to go away, because what I want to do is when the loop gets out far enough, I want to stop it so I can show you something. Dun 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 dun. Okay, that's good enough. Okay, sorry about all that dancing. So you see it out here in a coronagraph, right? You see that loop? That should be pretty bright. Do you see a little bit of stuff in front of it? In front of that really bright, whoops, not that far out. A little bit of that stuff, yeah, out here in front. This stuff out in front, that is a shock wave, or as close as we can figure to a shock wave. This is that front which is being driven. We call the CME, the solar storm, the driver. You oftentimes hear scientists say the ICME or the CME is driving the shock. That shock wave, which is being driven by that CME, created by that CME. Think of this CME as like a supersonic jet going through air, and it creates a shock wave in front of it, a sound, when they break the sound barrier. If you're going faster than the speed of sound, you got to have a shock wave that stands off in front of you. Same kind of idea here. This ICME is moving way too fast for all this slow plasma in front of it, so it creates a shock in front of it. It's kind of like it's breaking the sound barrier, and it's got to drive that shock out. That shock, however, everything is electrified. It's got electric and magnetic fields in it. That shock wave actually is a source of of acceleration for these particles, for the seed population that the solar flare created. So if you have just a solar flare, sorry, I'm dancing again. If you have just a solar flare, you have something that is here and gone, right? You got a seed population, but then it dies. But if you have a solar flare and a coronal mass ejection is launched at the same time, a solar storm is launched at the same time, look out, because now you got a second source that will accelerate these particles to even higher energies and spread them out. And we'll talk about that. And when they talk about CMEs, where this is part of this, let me go on this side, we're still trying to work out the theory of how all of it works. But because these CMEs, they drive these fast shocks, these shocks can now accelerate particles to way higher energies than we see just with the flare alone. There's something called the streaming limit, and some of the details of that are still being argued to this day. But I won't go into the details. Let me get a quick drink of water here. Okay, so some of you probably recognize this. Those of you who have taken, I should say, show of hands. I do that with the Millersville group, but I can't do this here. Show of hands, how many people take the flare course? If you've taken the solar flare course, oops, this side, you will recognize this diagram. Not this exact diagram, but you'll recognize what it means. It's pretty much the standard model of solar flare magnetic field reconfiguration. And for those of you who haven't taken that course, I will go over it just a little bit. Not a lot, but just a little bit. So you have the sun here. We're looking at the sun kind of from the side, so that's the limb of the sun. So this is something sticking off the edge of the sun. They're trying to show kind of a little bit of the magnetic field. So what happens is that you have a loop on the sun that is really close to the surface, and this loop will actually pinch in, and I'll show a better picture of it in a minute. It'll actually pinch in, and as this loop pinches in, it will tear off. It will have something we call reconnection. It will pinch off and create two loops suddenly that are disconnected from each other. And let me see if I can put my hands where it was more relevant. Okay, here we go. Right here. So at this point here, you have basically a pinch, and then this part goes down, and then this part lifts off. Okay? And that's why you see those arrows going down. Okay? So there's a lot of stuff going on, and I'm not talking about all that stuff. Most of that stuff was talked about, as a matter of fact, pretty much all of that stuff was talked about in the 4 or 5 solar flare and radio burst courses we've had. So we go over it in great detail. The only thing I didn't really talk about much was right up here where it says electrons. And you actually show the little, see the helical, see our little slinky? Those spirals, that's the electron beam going off. Okay? We have electrons, but we also have protons that get sent off. And well, and if I look down here, also he made the point. This is from Mihir Desai. I should have mentioned this. Mihir Desai who's a really savvy colleague of mine. He did a summer school, I believe, and this is he's an energetic particle person. been doing it his whole life and really, really savvy about it. And I was just reading one of his bullets that he had put down here saying that you get helium. You don't just get electrons and protons. You also get helium and heavy ions like carbon and all the way down to iron. And you can get ultra heavies, which I'll hopefully have time to show some of the ultra heavies because it's really kind of cool. You know, with masses greater than 100 atomic mass units. Anybody who looks at a periodic table, you know what I'm talking about. So it actually does happen through the solar flare mechanism. And for those of you who are familiar with the flare course, you probably recognize this diagram. He took this diagram and it was really nice because what he did was that, you know, not only do you see the radio bursts, you see up here, the top here is the 100 to 500 megahertz radio bursts and on up. You know, sometimes we get them into gigahertz, obviously, and well, that's 500 megahertz, of course, is. Then we have microwave radiation, or microwave radio bursts rather, showing a little bit of a profile as time goes on from the start of the flare itself down here at the bottom to what looks like 30 minutes out. So you have your really energetic stuff, the big radio bursts, plus type 3, which goes out into interplanetary medium due to a coronal mass ejection being let off. I won't go into that. Again, that's all from the solar flare course. Here's your microwave radio burst. Here's the H-alpha emission. Here's the EUV. So this is now the ultraviolet stuff. Once again, this is all light being let off. It shows you when it kind of brightens and then dims on the timeline of this. You can see soft X-rays, how they brighten and dim. Hard X-rays, how they brighten and dim. And then way down here at the bottom, oops, so this last plot, okay, you see where the electrons begin to rise. See that? Half an hour or so, okay, and these are all Earth observations. Half an hour or so after the solar flare, all of the dynamics of that solar flare happen. Basically everything that happens in this picture happens at the sun. All of that stuff reaches us in 8 minutes if it has no mass. So all the light, all the electromagnetic light, all the sun screaming, all of that stuff, the EUV emissions, all of that reach us in about 8 minutes. But the particles have mass. And the electrons have the smallest mass, so they reach us first in about half an hour. The other heavier stuff reaches us later, okay? But that's one of the cool things about electrons, having electrons be sent out with all those protons. Even though we call it solar energetic particles and solar energetic protons, we don't care so much about the electrons. They don't really affect us nearly like the protons do. For instance, in that coronagraph image, and you saw that blizzard, those were all protons. Electrons don't do that. They're just not massive enough to really bother us. But they sure are nice to see first because they give us a warning that the other ones are coming. They also give us a warning as to how much, how fast they rise, how high they rise. That tells us how fast the protons are going to rise and how high they'll rise. So they are a little bit of a warning for us, maybe about half an hour. And there's actually some models that are based on that. But again, for those of you who've seen the solar flare mini courses, you'll recognize precursor, the impulsive phase, the gradual phase, and you'll know what all those are about because we went over this in great detail. The impulsive phase is when you see the flare. The gradual phase is when you have the, you know that a coronal mass ejection is associated. So in this particular event, we have both the solar flare and a big solar storm being launched at the same time. And that means that this radiation storm ends up being massive. Okay. Again, for those of you who have seen the solar flare courses, and as a matter of fact, the coronal mass ejection courses, you'll recognize both of these images. Okay, this is very much like what we just saw, and I just wanted to remind you of the actual images that I showed in the solar flare and coronal mass ejection courses for continuity, because I want you guys to remember, oh, okay, that's what it is, that's what it is. So if I go over, oops, let me go on this side. Here's the solar flare loop. Remember I said we have the two loops. You have the two magnetic field configuration where you end up having it pinch in the middle and it takes off. The bottom part goes down. The top part lifts off and becomes the coronal mass ejection. Okay? And then this side is just kind of an example of that. I'm going to stand over here where on the side that I'm standing in front of, that red, the darkest red loop, you know, the bright red loop there, is now this yellow loop. Oh, actually, my fault. No, it isn't. My fault. The yellow loop on this side is actually the part that escapes on this other diagram. Right here. This part that escapes, the CME, right here, the solar storm that lifts off. Okay, that is what this yellow loop is. Brain fart for a moment. So the red loops are what actually fall back down to the sun. They're below those little red explosion, pop, 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 those 3 pop, pop, pops. The red loop is what falls down. The yellow is what lifts off as a coronal mass ejection. And interestingly enough, this is the diagram I used in the solar flare and the coronal mass ejection courses, but what I didn't talk about back then, see this? See these open field lines right here next to it? These are Archimedean spiral lines. They're supposed to be anyway. See the little helical stuff? See, right? Remember our little slinky? I didn't talk about them before. Remember, we were talking about slinkies as coronal mass ejections, but now I get to talk about the slinky from the point of view of being helical field lines. That, you know, not helical field lines, helical particle motion going around that solar wind. So as it's taking off, those particles are following that field and being shot out like that, like a big rocket, but they're kind of going in this trajectory. So we didn't talk about that stuff before. I just kind of ignored it. But that's what they're showing here when they're talking about this stuff taking off. Okay? They're actually talking about, let's see, what does it say? Escape particles. That's, if you can read that, it's what it says, escape particles. So that's a solar radiation storm being born. So you can have a solar flare, a coronal mass ejection, and a solar radiation storm all being launched at the same time. Bam, bam, bam. And now, you know, no wonder meteorologists get confused. What do they call it? Is this just one thing? What is this? No, there's multiple different phenomena that all can happen at the same time. They don't always, though. So you can't say, oh, well, they all happen at the same time. You should just have one big, you're just one big happy family. No, they're not. They don't always all happen at the same time. It's really the biggest events in which they happen all at the same time. But it's not a requirement. So just be aware of that. They are associated but not connected, and they're not causal. Okay? Let's see what I do here. Do I need this? Yeah, I guess I could. So what I've done on this side, yeah, let me stand over here, I guess, right? Yeah. So you recognize that that's still the same picture behind me. That is the solar flare thing. But now as you take that CME and you shoot out from the sun, there's the big solar slinky that is now the CME. Okay, don't think of that as the particle paths. That's not what we're talking about. That's the actual CME that's coming out. But you notice that it's driving this shock, that black line. Okay, that's a shock, and here's Earth down here at the bottom. But you notice that there are these other lines that are off to the side. Those are supposed to be the Parker spiral lines. Remember the spiral we talked about? Those are the Parker spiral lines that are kind of being distorted and pushed out of the way as this big, you know, massive CME is coming out. Okay? So they're kind of distorted and they're being pushed a little bit, but look how they wrap kind of around, just in that same Archimedean spiral thing. They kind of wrap around a little bit. So these aren't straight lines. It's not like they come straight out of the sun, straight down. They wrap around this structure in that Parker spiral-like thing. This is why I wanted to show you the Parker spiral from the very beginning. You got to get your mind thinking about this, you know, the sun here looking down the North Pole, and if you have a big structure coming out of the sun, it's got to make that magnetic field that's in this Parker spiral pinwheel, right, this Archimedean spiral, it's got to push that stuff out of the way, or it's got to plow through it, or it's got to move them out of the way. And so those lines don't lose that shape. They just kind of get distorted a little bit. But it's very, very important, because when you think of your particles, your little slinkies, now not the CME slinky, okay, so I'm not talking about the red slinky, I'm now talking about particles spiraling around these Archimedean lines. They're jailed, right? We've got a magnetic field, they're jailed to wrap around, you know, to spiral around those field lines as they come out. So as they come out, they're going to be guided in a very particular way. And notice that here at Earth, the field lines look like they're, you know, they would be coming radially from the sun, like straight down. Notice the field lines that connect back to the sun that hit Earth, they're way off here they're way over here on the edge of the sun to the west. This part of the sun. They're not down here. They're not over here either, necessarily. Most of them are all the way over here. And they wrap around the structure. Give you an idea that maybe particles being shot out on this side of the sun will hit Earth, but particles being shot out on this side, maybe not so easily, meaning this side, right? Those field lines aren't anywhere close to Earth. They're out this way. They spiral out like that. So it gives you an idea that, maybe there's something special about this. And there is. So let me take a moment. Let me see, is anybody lost? Anybody you guys understand this thus far? Let's see. My video is so far behind. My video on my monitor here is so far behind where you guys are. I'm still looking at the particle acceleration and solar flares thing. I hope the comments are caught up. Stop pretending you don't understand my questions. Where can I see Planet X? Oh, for goodness sake. This is not about Planet X, guys. If you have, look, if you're going to be on this feed and distracting my students, please get off. You want to do a Planet X course, go somewhere else. I am not an astronomer, okay? I'm a space weather physicist, and this is a course about space weather. Please be mindful and respectful of the students who are taking this seriously. I am not going to address Planet X here. Go talk to an astronomer if you want to talk about Planet X. Planet X doesn't affect Earth. So please, we're talking about space weather. And it's a very specific course, and in this case, with radiation storms. Nothing to do with Planet X. Okay. I love watching Dr. Scove. Thank you. Not lost. A few questions, Tam. For the most part, I get it. Okay, good. I'm seeing people say these types of things. Good. I'm glad. And we're going to continue going into how the I See Me changes the structure. Because you're not the only ones that were lost. Oh, my question was not for you. Okay, well, just as long as you're asking, Mandelbrot said, as long as you're asking questions that are not distracting others, because what happens is I get students who come to me afterwards and say, why were these people filling up the chat with questions that were irrelevant? If you're getting relevant answers to your questions in the chat, I don't care what you ask. But please don't, upset people who are trying to pay attention to the lecture and take up space arguing about stuff that really isn't relevant to this course. If it gets out of hand, it becomes a problem, and I don't want that. I want everybody to be able to talk freely, but I also don't want to distract too much from the course material that I'm presenting. So, please just be respectful in the chat. I appreciate it, because I don't have anybody doing a moderation. I just trust everybody's on the, the Good Samaritan kind of set here. Okay, good. I'm glad. Oh, good. I'm so glad, LeBlanc. You're going to watch from the beginning. Okay. Ignore the trolls. Yeah. Well, again, those of you who get annoyed, let them know. Say that in the chat and say, please take some of those questions. If they get too detailed, take those questions offline if they're not relevant to the course. It's not that I don't want you discussing them. Please just take them offline if they get too distracting. So everybody chime in if it's too distracting. If not, have at it. I love discussion. So, okay. Good. Everybody seems to be, you're welcome. You're welcome, Ruby. Let's see, and Rising Green, thanks. Okay. We can block the trolls, understood. I don't want to, I just want people to be respectful. Yeah, that's great. I'm glad. Claudia Albers, you're watching. Fantastic. Ask some questions if you need to. You are a bit different than me. Your expertise is very different than mine. So it's interesting that you've joined us. That's a surprise, and thank you, I guess. Okay. Stay on track with your teaching. Yes, sir. Oh yes, Claudia, I will. I will. Okay. So what I'm going to talk about now is, again, I'm keeping the slinky here because you can see behind me there's slinkies. Again, these are now particles. Okay, this is particle trajectories. Since there's a physicist in the room, I will mention that this is one of the reason why particles travel like this that are charged is what we call, it's one of the 3 adiabatic invariants. And I'm not going to go into what they are, but if anybody who happens to be very ambitious can go Google adiabatic invariant and take a look at what the adiabatic invariants are. It teaches physicists quite a bit about what laws are being broken and why, and it happens a lot, especially in the Earth's inside the Earth's magnetic shield. Having adiabatic invariants being broken, for example, because there's a lot of times you can't. That's why they're invariant typically. But when they're broken, it means a lot. It means a lot of, for instance, energetic particles being dumped, and the radiation belts, for instance, losing a lot of their trapped radiation. But this is just one of the adiabatic invariants where particles are jailed along the field and they have to spiral along the field. So we will continue talking about that because it kind of guides your eye a little bit. But for those of you who saw the course, or my courses on coronal mass ejections, you guys know that one of my dear esteemed colleagues, Jack Gosling, who is a thesis advisor of mine, he wrote a paper in 1993 called The Solar Flare Myth, which is title here, and it really lit up our community. So even back in the 90s, we were still trying to argue the concept of whether solar flares and coronal mass ejections were even considered different, because at the time they weren't even sure that they should be distinguished. And this was another touchy point when it came to solar radiation storms. You can imagine if you have a solar flare and a coronal mass ejection and you're not even sure you should differentiate them, because every time there's a solar flare, there's a coronal mass ejection. There's a big solar storm that's launched. No, no, no. That's what Jack basically said. Said, no, they're completely different phenomena. You can have a coronal mass ejection without a solar flare. You can have a solar flare without a coronal mass ejection. And he helped dispel the solar flare myth. The problem was that it was already so entrenched up to the, you can see where it says here, whoops, up to the 1990s. And really what they meant was because of the solar flare myth, they started breaking away from this concept that only solar flares created solar energetic particles events. And so what they're showing here is a really provocative diagram. If any of you have a dirty mind like I do, you know what I'm talking about. But it has a very provocative, I would never have drawn this picture. No, too embarrassing. Provocative view of what a solar flare ribbons look like. My apologies. Don't shoot me. It's not my diagram. And then they're showing particles coming out, spiral particles or spiral paths, helical paths coming out from the sun along the Archimedean spiral, okay, or around the Parker spiral, and so they're saying, okay, back up to about the 1990s, from essentially the 1940s, when Forbush was first looking at Forbush decreases and understanding how got to be careful because those are more about galactic cosmic rays, but understanding how the magnetic field affected energetic particles in the solar wind. And I'll go into Forbush decreases, just not in this class. It'll be probably one of the next classes, because it is about solar radiation storms. Radiation storms, but only cosmic rays. At any rate, but in the 1940s, we were kind of really trying to figure out how this stuff worked. And from about that time up to when Jack did his paper on the solar flare myth, we believed that solar radiation storms only were caused by solar flares, and that we had a picture very similar to this, where you have this very localized point on the sun and you have particles shooting out right from that. And so it was a very narrow beam in a sense. But then, as we realized that, okay, solar flares and coronal mass ejections aren't the same thing, and they don't always happen concurrently, they had to modify their picture. And I guess maybe I'll stand on this side? No, I'll stand on this side. So what we realized was that we actually had to break it up into 2 different classes, because as we started looking at solar flares and started looking at solar radiation storms, only from solar flares or solar radiation storms when there was a big coronal mass ejection or solar storm involved. We started seeing differences. And so we started labeling them according to a solar flare only, and we called them impulsive events. Okay? And that's the same picture as you saw above. And then, but there was this, when we realized that there were different types of radiation storms associated with when there was a coronal mass ejection, we labeled them gradual events. And the reason for that was because you can imagine the gradual events were more gradual, oftentimes more gradual to rise and much more gradual to fall. They lasted longer and oftentimes were more intense. Their peak intensity was much larger. And what we realized was that with solar flares, the acceleration was always happening in the lower atmosphere, right at that region. Remember I showed you that standard flare model and you saw the particles leaving? Yeah, that's the seed population, what we call the seed population. But when you had a CME, especially one driving a shock, suddenly the whole picture changed because you took that seed population and now you did something else with it. You actually drove through that shock and accelerated those particles even more and spread them out and scattered them. So now you have a picture where you have this, and again, we're looking down at the sun. In this case, let me go over down here. Look at the sun, the northern pole of the sun, okay? You have the Archimedean spiral again. That CME is just, they've got this little pancake thing, this little, excuse me, the little orange, like, I don't know, hot dog. It's just a cut through it. It looks kind of like a hot dog. And then the black line is the shock in front of it that it's driving. Okay, it's obviously a little bit of a cartoony thing, but you can see that. And now, instead of just having a very narrow beam of energetic particles coming out, now it's spread out over a large swath of that Archimedean spiral, because the particles can actually travel up and back in that shock. And I'm not going to go into the shock physics. Trust me, you don't want to know about the shock physics and transforming into different coordinate systems, ranking Hugonio and all this other crazy and the quasi-linear theory. And I mean, you've got all sorts of stuff. There's quasi-parallel shock properties, quasi-perpendicular shock properties. It's a hell in math. And that's not really what the point of all this is. I think it's good enough to say that these shocks act as particle accelerators. The particles, actually what happens is that they cross through the shock once and then they get sucked back in, so to speak. They have to curve back in, and then they go through the shock again, and they go back around and shock again, and so they just keep going back and forth through this shock and get accelerated time and time and time again. And as they do that, they actually wind through the shock and get scattered all the way around to these different areas, these different parts of the spiral field line. By the time they finally escape the shock, not only are they super particles now, they're super energized, but they're now at a different longitude. They're now, at a solar longitude that's way different. So they may have started over here, and now they're over here. Or they started over here, and now they're over here. So that's the kind of crazy thing about getting a CME involved, is that it totally changed the picture of what a solar radiation storm will be. And the neat thing, of course, is that as the scientists were beginning to find out this kind of stuff, Hillary Kane did an amazing contribution. She's now retired, but she made an amazing contribution to this part of the field, especially with radio bursts. Her and Ian Richardson were a stellar team when it came to energetic particles and superthermals in the solar wind, as well as Forbush decreases and other stuff. But and so did Kaler. I mean, these guys are just pioneers of the field and just made wonderful contributions. It ended up being that anytime you saw type 2 and type 3 bursts, and you knew that you were going to have a solar radiation storm coming, you knew what kind it would be. You knew it would be a gradual solar or gradual radiation storm instead of an impulsive one. So now, to this day, we have, for those of you who really are interested in the details, we have a two-class picture. And this is from Ream's paper in 1995. He did a really good review. He's done several really good reviews on solar particle events. We have the impulsive SEP events and the gradual SEP events. And here's just a table from his picture or from his paper of 45 different events. And you can see for impulsive on the left, gradual on the right, You can see some of the particles. You have a helium ratio. So we have what we call isotopes of helium. There's a particular ratio that you see in impulsive events that you don't see in gradual events. Impulsive events have a tendency to be electron rich, where gradual events happen to be proton rich. That's why we worry far more about CME and solar storm based particle events. They're also picking them up from the solar wind. So the seed population, it can be a what we call a superthermal population, and then because of that shock be accelerated to higher and higher energies until they become relativistic. Whereas with the impulsive events, they only get the seed population right from that shock or right from that flare, and that's it. There's no acceleration. There's no further acceleration. So they're oftentimes much more electron rich than the gradual events. Also, when you come into heavies, and an iron, here we're looking at iron to oxygen ratio. So we use certain elements as like a standard candle, and then we divide, how much more is the ratio of this element to this element to kind of get an idea. Sometimes the abundances are so low that it makes more sense for us as scientists to do a ratio of the abundances to get a better feel for something. Because remember, these things are very vacuous. These are collisionless plasmas that we're seeing. So the ratio, or so the number of particles that we're seeing, irrespective of whether it's protons or some of these higher elements, these heavier elements, they're very, very low. So that's why you see things written as ratios, because it helps us as scientists understand them better. But you can see the ratios are very, very different. Iron to oxygen ratio is very different. So is the hydrogen to helium ratio. And the QFE is the charge state of iron. Iron is one of the standards that we use. And you can see there's even different charge states. So it means that, what that means is that there's, where the source population is in the atmosphere of the sun, it's different. It's at a different temperature. We know that because the charge state is different. Charge states tell us, for these particles, they tell us really how hot something is. If an atom is extremely hot, it's going to have more of its electrons ripped off. It's going to have a higher charge state. If it's colder, then it'll have a lower charge state. And so it tells us where in the atmosphere the source of that particle came from. And so you can see they actually do show that they're slightly different. And then we have other things, the longitude cone, how widespread. You can see with a gradual event, it's 180 degrees. It can be half of the sun or more. And I'll show, probably not in this class, but in a later class, you'll see a Carrington class event from 2012, and even the one from 2017, where the radiation storm was seen more than 180 degrees in longitude. And this was just recently. So, we get these radiation storms this intense and this widespread quite frequently. And then, of course, you have things like your radio bursts and whether you see something or not, how many events do you have. You can see that impulsive events happen a lot more times than gradual events. But, the gradual events are the ones that we really care about. And then here's a look. So we're getting close to 1 o'clock. Here's a look at what these events, let me stand on this side, what these events may look like in the solar wind. I'm thinking, well, maybe I will stand on this side. I try to cover that sunlight, but instead I'll stand here. So here are two events. Here's a gradual proton event, so a gradual event with a CME. Here's an impulsive event on this side, okay? And it's a timeline, in this case, December 5th. These are days. December 5th, 6th, 7th, 8th, 9th, so that's 4 days. Here's August 13th, 14th, 15th, 16th, 17th. Remember, time runs this way. What you're looking at is intensity, the number of particles. In a sense, it's really flux, I think. Yes, it's flux, so it's a number of particles that goes through a particular detector that's about, that's however wide they want to make it. That's really the only difference between amount, total amount, and flux, is that your flux is really how much is going through a particular geometry, a particular space, poke myself in the eye, how much is going through a particular space at a particular time, in a particular amount of time. And it really, in this case, it's simple enough to say, well, that's the amount. It's not the total amount, but it's just, it tells you the rate, it tells you the not the intensity, but just tells you how many particles are going through, how many particles are incident or hitting the detector at any one time. And so you can see in a gradual event, it's, it ramps up, in this particular gradual event, it ramps up pretty quickly. And then you're looking at multiple different species. Or no, sorry. Well, you are and you aren't. You're looking, I think the label is the same. So you're looking at electrons and as protons in different energy ranges. So the lowest flux on this side is going to be, looks like 22 to 27 MeV protons, so really energetic stuff. And then slightly less energetic has a slightly higher flux, and then less energetic has even a higher flux, okay? And then you actually see a little peak here at the end, and I'll talk about that in a minute. But you can see the gradual event, look how long it lasts, and how even with the low energy stuff, how and when I say low energy, I mean relatively low. These are still MeV. So these are still relativistic particles. They're just not 100 MeV. But these particles are lasting for days and days and days, right? In an impulsive event, look, it doesn't even hit. If it lasts a day, from the August 14th to the 15th, we're lucky. I mean, the peak of it lasts a very short time, hours. Remind you of a flare, right? They last for a very short time and they're gone. But coronal mass ejection driven ones, these gradual ones, are gradual and they last and last and last. And why is that? Anybody who's taken the CME course knows that shock is driving out and driving out and driving out in the solar wind until it hits Earth. And then the shock's on the other side of Earth. It's behind Earth. Once that shock passes you, and that shock is the source of accelerating those particles. Once that shock passes, well, it's gone. It's, now it's driving it further out, and Earth doesn't see it anymore. Believe it or not, and I bet you, this peak here, in this gradual event right here, this peak, that was when the shock passed Earth. That's when it hit our upstream monitors. And then after that, the particle event dies. It just fades off. But until then, until that ICME, until that coronal mass ejection ends up hitting Earth, and that shock is still driving particles, and it's still sunward of Earth, you will be bathing in all these particles in this gradual event. But you don't have that with an impulsive event, okay? Because there's no CME, there's no solar storm that's driving a big shock in front of it. You just have the flare particles, bloop, and they're gone, okay? Not the same with a gradual event. I hope everybody understands that. Okay? Oh yes, it's shorter bursts and over. Good. Good. So I might just stop here. Let me stand on this side. Hopefully this will play over and over again. So when I've got this model here, you can see it kind of like the flare model, the traditional model. This would be more like, I won't say an impulsive event, but kind of like an impulsive event. And then this model here is more of what you would expect with a coronal mass ejection involved. So with the flare model, you just have kind of a narrow beam. It's driving out over a few solar longitudes, these particles, as they are shooting out across a single, say we're doing a single Archimedean spiral, okay, line, and the particles are coming out, okay? And here, along that same single Archimedean spiral line, but now you have a coronal mass ejection, and that line is threading it. Okay? And look how much more spread out those particles can be. Simply because you have a shock that that's driving it, and it can cause those particles to scatter in front. And it makes a huge, huge difference. So you can imagine, up until the 1990s, we only thought that this was the picture. And then we finally figured it out, that it wasn't just the flare that caused these things. It was actually the CME that actually ended up making them, believe it or not, in many cases, not just wider, but more intense. You can't see that here. You don't see an intensity change. But you do see, as a matter of fact, it actually looks like the CME is weaker, but you do see the longitude change, and that's what I wanted to show you, was how much more widespread. So, but there's two things here. One thing I'm going to hint, and I'm going to hint to at the next course, because I think I will stop here in just a moment. But do you notice that if Earth is down here, let me go. Earth is right here at the tail end of this magnetic field line, right there at that part of the spiral. And the same thing on this one. If I go here, you got that field line right here, and Earth is right here, okay? down here at the bottom. Um, what was I going to say? I lost my train of thought. That the source region of these events, of these solar particle, these solar bursts or the radiation storms, are not straight down. They're not straight down from the sun. They're off to the west. Okay? Because of that Parker spiral again. So if you take nothing else away from this course today that you can carry with you to looking at radiation storms in the past or in the future, when I talk about the Earth strike zone, when it comes to radiation storms, you will always see me talk about it being the west side of the sun. And when you see Space Weather Prediction Center, when they talk about radiation storms or the prediction, the probability of having a radiation storm, when you see a sunspot, an angry sunspot, when it's at the east side of the sun, so I'm staring, if I'm the sun, and I'm staring at you, and I have an angry sunspot here, and that sunspot fires a solar flare, and then it fires a CME, and it fires a radiation storm, and it fires all of it, because that's what these angry sunspots do. They're just bad actors, and they just keep firing as they rotate across the solar disk. You will see the radiation storm predictions, the possibility, the probability of having a radiation storm go from essentially zero or very low to very high as this thing rotates to the west limb. Why? Because of that Parker spiral. Okay. We will get in next time, and I didn't get as far as I wanted to, but we will go next time into what the longitudinal differences are. So I will even move forward here just to show you a little bit of, let me show you that really fast. So you will see, and I will go through this in great detail next time. These are all traces. All 4 of these are different examples of what a solar radiation storm looks like. But the source is launched, the source of those radiation storms is at a different solar longitude. Now, no, it isn't done in the way that you think this is over here, that's over here, that's not, it'll be confusing if you think of it that way. But look how radically different the traces are. Do you see how radically different the traces are? So we will get into that. And it has everything to do with how are you magnetically connected to the sun. And that has everything to do with this here. Okay? So I've talked for, looks like 2 hours. I think I will stop. No, I didn't get as far as I wanted to. Bummer. But hopefully we've gotten a good start. So what may I, do you guys have any questions? Let me stop there. I wonder if this is going to be too distracting, having me have this model keep running. Let's say thank you. You've actually helped me unstress the changes I need to see and feel them. Oh, good. I'm so glad. Thank you. How did GCRs fit into this, if at all? GCRs do fit into this picture. We're not going to we didn't get into it in this thing, but I will be talking about GCRs starting maybe the next class. It looks like we're probably going to have at least 3 courses on radiation storms. I will be talking about GCRs. It's very, very, GCRs are a huge part of all this, but they don't come from the sun. So the sun actually helps shield out GCRs. However, CMEs, actually, well, yeah, this side, CMEs, they actually help shield out GCRs as well. So strangely enough, when we talked about Forbush decreases, the same structures that actually cause solar energetic particles to spread out and be worse are actually what helps shield us from galactic cosmic rays, because they create their own little magnetic bottle that the GCRs can't penetrate. So that's where we get this Forbush decrease. It's really, really fascinating stuff. So what causes inclement weather, space weather of one kind, can actually aid in slowing down or minimizing space weather of a different kind. You see that a lot in space weather, where the sun, like for instance, solar maximum, is horrible in the sense that you have a lot more solar phenomena occurring, and the space weather is worse from a solar standpoint. But the solar magnetic field, the solar shield, so to speak, it actually is stronger when it's solar maximum. So it shields out more of the galactic cosmic rays. So the galactic cosmic ray environment is actually simpler. It's actually easier and more minimized during solar maximum. And it's actually solar minimum when our sun is quiet and the shield is weak that more galactic cosmic rays leak in. And so once again, there's that thing that what makes one kind of space weather better makes another kind worse, and what makes one, and then it reverses. We see that a lot in space weather. There's always inclement space weather. It just depends upon what the source is that you're looking at, whether it's solar or, let's say, intergalactic. Hopefully that answers the question. Are the heavy metals created in the CME or only distributed by the CME? Only distributed by the CME. As a matter of fact, I'll give you a little hint since you asked that question. Let me show you something cool. Wait, where is it? Hold on. You guys get to see a little bit of the dirty laundry here. Where is that slide? There it is. Can you believe I picked it out and all that? Do I know my stuff or do I know my stuff? No, I've just been looking at the slides a lot. I haven't made this one ready for consumption. This is once again Mihir Desai's slide. But for those of you who have not seen, or who are sticking with me through this whole course, I'll show you something really cool. Here are the heavies and ultra heavies for these ion abundances, and you can. Well, I'll stand over here. You can see, we've got mass ratios or atomic ratio or atomic mass units, 180 to 220, all the way down. We've got iron, silicon, magnesium, neon, helium. You see it all, and then it goes higher and higher and higher with less abundances. But you can actually see that we have that. But here, this plot is the one I really loved. So here is counts per bin. This is just a raw histogram, and I forget. This is from ACE, Ulysse instrument. So measuring in the solar wind. So it's counts per bin. And if you look at the mass ratio, or the atomic mass units, as you go across on this side, look, here's the distribution of ultra heavies. I'll see if I can circle it. It's this little grouping right in here. A little bit lower. Right in here. Yeah, that group. Okay? See that little bump on tail, that little extra stuff? You know what 197 is? The atomic, anybody familiar with the periodic table? You've got I don't have the periodic table. Oh, there it is. Here's the periodic table. Anybody know right next to what PT is here, right next to Mercury? If I go over this way, I think. Recognize this? 197 mass units. You know what that is? It's the most valuable currency. It's gold. There's gold raining down on us. There's gold in them there, star. Or solar wind. They say, oh my God, it's full of stars. Well, oh my God, it's full of gold. Our solar wind actually has gold in it. When a solar radiation storm hits, you are being sprinkled with gold. Is that amazing? I found that just utterly fascinating. But this is how we get all of our heavy ions. This and supernovas and stuff like this. And yes, our own star is making it. And every time you get a solar radiation burst, you can think, oh, I'm just that much richer. By a little bit. So hopefully that will send you off with a smile today. But I will talk more about this in the next one. Jack Gosling abstract was very interesting. I read it many years ago. Yes, I love Jack. God rest his soul. He was such an inspiration to me. And I am very grateful to say that he was part of my graduate career. So, hi Adrian. Let's see. Does that mean flare-based radiation storms are potentially more powerful, concentrated in particles, than CME-based? No. Or is it the opposite because of the CME acceleration? Opposite because of the CME acceleration and the fact that they're gradual. So these events are they last so much longer. So what happens is that when you get a CME and it's launched, let's say along with a solar flare. So now let's say we have a solar radiation storm. Remember, it doesn't always happen that way. There isn't always a solar flare associated with a CME. There isn't always a solar radiation storm associated with either of them. But let's say in this case there is. And so you have a solar radiation storm that's coming. That solar radiation storm, it will start in about, depending upon its electrons or protons, because the electrons get there first. It'll start about half an hour after the solar flare hits, or after the solar flare is hit, and then maybe it's dying down. You start seeing the electrons rise. Then about half an hour after that, so about an hour later, you get the protons start rising. It depends upon where the solar source was. If it was on the east limb or the west limb, stuff like that, we get into the next class. But from the start of that solar radiation storm, when you see it, if part of it's being driven by that CME, you're going to be stuck with that solar radiation storm until the CME hits you. And that could be days, right? With a really fast CME, you get a really fast shock, so you're going to have a really strong storm, but it'll only take 2 days for the CME to hit. But for slower CMEs that are still driving shocks, so we're talking maybe 3 days, 3.5 days, you can get weak shocks. Those, you'll have to deal with a radiation storm with high intensities for 3 days. That continues to build until that shock passes. So those are far more painful for navigation, communication, not power grids. Power grids don't care. I care about radiation storms. But, people working in space, satellites, all of those things that care about radiation storms, they are affected far more by CMEs, or, by CME-driven radiation storms, simply because they last so long. So hopefully that answers that question. Dr. Scove, any thoughts on the increase of in UV radiation levels? UV radiation levels in what? The increase in UV be due to what? Coming out of solar minimum? I'm not sure. Increases in UV radiation levels here at the ground because of climate change, because of the drop in ozone? Not really. I stay away from climate science simply because it's very complicated. And so I don't know. So maybe clarify your question, and I'll see if I can answer it. But if it has to do with climate science, I probably will skirt it, just because that's not my expertise. And I'm very humble. I know a lot about what I know a lot about, and that's not a very large swath of anything. It's pretty much space weather related. I can speculate on a few things, but I will definitely call it speculation. So, okay. Anyway, how do the heavy metals interfere with the radio frequencies? No. You probably get more of that from meteor scatter. If you have these meteors that are coming in, they probably have, with all the particulates up in the upper atmosphere, as the dust kind of causes issues. That probably is more laden than any of the particles that you see coming in from solar radiation storms. So, if there were higher abundances, then I would say, well, then the metallic dust would probably increase conductivity in the atmosphere, and you get more ionization, you get more, you get better propagation. But I honestly think that these radiation storms, they're so vacuous that you're not going to get anything regarding that. If anything, the radiation storm itself, because of the cosmic ray showers, because you're getting all sorts of other little particles, will just cause a lot of hash and noise when it comes to radio propagation. So even if you did have a contribution with the heavy metals helping conductivity, it would be washed out by all the protons, the pions, and neutrons, and all the not neutrons, but pions and what I can't even think of it. I have to think of all the components of a cosmic ray shower. Let's see. Hang on. Do I have a plot in here that shows it to you? Oh, poop. Oh, yes, I do. There it is. Look at that. So one proton can cause all this nightmare in a cosmic ray shower. How's that? You got 3 components, the muonic, hadronic, and electromagnetic components. See why I didn't remember it all? So you got muons, you've got pions, you've got, I don't even remember what the K stands for. And you do have neutrons. Okay, I was wrong. I thought you didn't get neutrons, but you do. And the hadronic component. And then, of course, you get gamma rays and electrons coming out. So, my gosh, there's just a bunch of stuff that comes out during a cosmic ray shower. So we call those daughter products. And those daughter products will completely swamp anything, because that comes from just one proton. So the daughter products will completely swamp anything. And I think I have a better picture here that kind of shows you, I'll stand once again on the side, that shows you the idea of how far some of these particles will penetrate. So you have the primary particle coming up here, which is typically a proton, and then you get all these daughter products, which then most of them get absorbed in the higher atmosphere, but so you have to go with weather balloons in order to even measure this stuff, or to even get the primary particles, so you can actually see the protons. But as you get to the point where you have like Concorde jets, and then even down at around 11,000 kilometers or something, where you get a lot of airlines flying at 40,000 feet, you don't see any of the primary particles anymore typically, but you do get muons, you do get electrons, you do get X-ray, bremsstrahlung, stuff like that. You do still get some of that, and of course the muons go all the way to the ground, and neutrinos and blah 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 blah. So I think at sea level you get a muon every couple seconds. If you have the right detector, you can see a muon pass through every couple seconds. And that's just natural. That's natural radiation down here. So hopefully that answers that question. Did the sun contribute most of the heavier elements to the Earth, or was that from a different star? That's a good question, and I do believe it was most likely the other star, because before our sun ignited, the planets were already forming. So we got most of our matter just from the accretion disk, and that came from many stars before our sun. So, I would have to say other stars other than our own, but our star is just like they are, and it's creating these elements all the time. So, it's part of a big engine, a big cosmic engine in that sense. Let's see, K Maison, thank you. I appreciate that, Scott. I'm not a high energy physicist. Once again, these are areas that are tangential to what I do, and I have a little bit of knowledge in them, but like Homer Simpson, when you put some new stuff in, the old stuff falls out, falls out the other side. There's only so much you can keep inside your mind, and you could get a PhD in any one of these areas. So I have absolutely no, I'm completely humble, and I have no ego about telling you what I don't know. And the K Maison, okay, thank you, I appreciate that. Oh, you're welcome, Preston, and thank you for telling me the course was good. I'm sorry I didn't get as far as I wanted to, but I hopefully you'll tune in for the next one, and I'll get through more, including the longitudinal stuff, which is good. And then I'll start getting into the examples, which will be really fun, because then you get to see some of the crazy stuff that has actually happened due to radiation storms. Why does a CME shockwave move so slowly? Because it's driven. A CME shockwave only moves as far out as it needs to, just like the shockwave of a plane moving supersonically through the air. The shock is only there, it serves only one purpose, and that is to change the properties of the material, of the fluid in front of it. I'm saying fluid for a very specific reason. Fluid in physics means something. It doesn't mean just liquid. It means something that behaves in a certain way. And a plasma does behave like a fluid, collisionless fluid, but still a fluid. Air behaves like a fluid too. But the shock is only there to change the properties of the fluid in front of the obstacle that's driving it, the driver of that shock. It has to change the properties of that fluid in front of it so that the obstacle can go through it and not get crushed, and not because what happens is that fluid, with the properties that fluid has, the properties are such that the particles couldn't move out of the way in time if they were just to stay the way they are. So a shock wave actually changes the distribution of energy inside that. So it makes certain particles faster and hotter, or it changes the direction, or it depends upon what properties it's molding, but it's physically changing the properties of whatever that fluid is between the pre-shock region and the post-shock region. So we say this pre-shock and the post-shock, we call it the shocked, literally the shocked fluid. It changes the properties so that those particles, that part of the fluid can be diverted around that obstacle. And that works, that's why you get a sonic boom. That's a sonic shock wave. You get light booms, for instance, when a light wave, let's say I forget if it's an X-ray or gamma ray, or I forget what it is, but it might actually be a particle in like aerogel. You can look at Cherenkov radiation, for example. And what it is a particle is moving through a vacuum at the speed of light, but then it actually, if it goes into a different material, like aerogel, for example, it has to slow down because it's actually moving faster than the speed of light in that material. So particles cosmic rays and things like this will actually, when they penetrate aerogel, will actually let off a blue cone of light. And that it's literally a light wave. It's like a light shock. It's a shock wave because of the properties of the speed of light. And it's the same kind of idea, that it's there are certain properties of a fluid that have to be changed in order for something that is moving too fast for that fluid to be allowed to work. And so you get sonic booms, you get light booms, you get, in this case, you get shock waves in space from a collisionless plasma that then change the properties of the material in front of them. If that driver slows down, then the shock wave may no longer be needed. If that driver speeds up, the shock wave will stand further off from that driver. So, because it takes longer time. So if this thing begins to speed up, you'll see the shock wave move out until it gets to what we call a standoff distance. And it's a balance of how far does that shock wave need to stand off to shock this plasma so that it has enough time to get around this obstacle. If the driver's moving slower, the shock can be closer because the particles don't need to be diverted as fast. If that thing is moving really fast, that shock wave stands way away because it can't shock and change the properties of that fluid fast enough for those particles to move out of the way if this thing's driving really fast. So it has to be way ahead of the driver of that shock. Same thing in the air with going Mach 1, Mach 2, Mach 3. When you have a jet that's flying and it's Mach 1, that sonic boom is going to be a little bit further out. The shock wave is going to be further out. If you're going Mach 2, it'll be even further. Mach 3, it'll be even further. Okay? Same kind of idea. There really is a very, very well-known pattern. So you can look at shock physics and understand that. So hopefully that answers the question for you. I think Dutchins pointed me into Dr. Scove's direction. Thank you. He's such a great guy. And I'm fascinated by his work, but I've never had a chance to sit down and actually watch. Because he's on all the time and he's talking about stuff. The only time I freak out is when he says that USGS scientists are chasing after his wife. Do you know how much USGS scientists get paid? They don't have time for that. They're not after him. Trust me. The USGS scientists, they're poor. They're having a hard time keeping their magnetometers working because the Congress wants to shut them all down. And it's like, wow. I mean, I know USGS scientists personally. They have no earthly interest. I can't even get Dr. Jeff Love, to even return one of my emails when I need him to. He's so overworked. He has no time gallivanting all over the country, chasing after people's wives because they're trying to link earthquakes to space weather stuff. Trust me, Jeff just looks at it and says, fringe science, I got proposals to write. I got way too much stuff to do. So if anybody can tell Dutchins that don't worry, his wife is not being chased by, and he is not being stalked by the USGS, please alleviate his fears. It's not happening. Maybe other people are, but not USGS, not anybody, not scientists from USGS. Us scientists, we're too busy. We've got our noses in books and noses in data. We're not that interested in that other kind of Mission Impossible intrigue. It's just not part of our makeup. So, but I love Dutchins, and I hope I sometime get a chance to actually look into what he's doing, because I've had way too many people tell me that there's something really magical about some of his theories. So who knows? It's one of the things I love about fringe science, right? It helps drive mainstream science in directions it might not have otherwise gone. So I really dig that. So, okay. If you do not bend your mind, nothing will be achieved. Agreed. Okay, guys, any other last questions? Quackademia, quack, quack. We need a few. We need some of that, because sometimes, look at dark matter. We never would have discovered dark matter if somebody didn't bother, a woman in this case, didn't bother to look at stuff that nobody thought would be interesting. So, and find, correlations that everybody else kind of just blew off. So, that's sometimes where the real gems are. And I have a tendency to really bite my tongue when it comes to that kind of stuff, just simply because I know there are gems in there, but it's just not low-hanging fruit. And so you're not going to get a mainstream scientist to go after it because they've got to get funded. They got to do stuff where they have an idea that there's going to be results. And we need people who are willing to do this on their own time and do voluntary work and try to make correlations that then help push out the frontiers. And most of the time it's wrong, granted, but every now and again somebody stumbles on something really fascinating and it changes paradigms. So I will always be someone that says that fringe science and mainstream science need to have that collaboration and need to have that handshake. And I hope it continues to happen for, the rest of my life and beyond. So, okay. Big Bang, all the fantasy lies. Oh, come on, Adam. Okay. Oh, I'm not gonna talk about that. Anybody else have any other questions before I go? I've now been on for 2.5 hours, so I want to make sure that I have a voice left. I've got to do a forecast after this for tomorrow, so I'm going to sound all hoarse for it. I would love to volunteer. Oh, are you asking me to volunteer? Ping me on Twitter or ping me via spaceweatherwoman@gmail, and we can chat. And we'll see, what you might be willing to do or what you're interested in. Please bring Dr. James Birch on your show sometime for an interview. Oh, from Sweary. I don't know. I mean, I know, I believe I've met him, but believe it or not, I don't know him very well. And if I get a chance to, it would probably be something like at AGU when I see him. I doubt that he and I would get much of a chance to interact otherwise. So, okay. When I win the lottery, I will fund your research. Oh, I wish I could now. Thank you so much. That's so kind. My big thing is to start this field of space weather broadcasting. And if we can get that off the ground and change the paradigm of what people think weather is, I think that's going to be critical. I think we'll save lives. And I think we'll make ourselves much better armed for our spacefaring future. And it's beyond time that we do this. So, I'm hoping by the time the next solar maximum rolls around, so that's in like 5 years, right? That we will be seeing credible space weather reports on television, pinned up right with the regular news, the typical terrestrial weather news, and it will be space weather reports that mean something, that will be actionable, not just look, aurora. No, something really credible. So that's what I'm working towards. Okay. Thanks, Jerry, and thank you for the phone call. I see you say thank you, Dr. Scove. Thank you for the phone call. That was so critical. And I'm glad that the audio, I think we got the audio taken care of. So I bow to you. Thank you. Thank you. And thank you from Wales. You're very welcome, Ron. Okay. The new satellites at the poles, what's anticipated? The new satellites at the poles? What do you mean? We have sun-synchronous polar orbiters all the time. POEs, for example, polar, nothing, no big deal. Oh, are you talking about with radiation storms? Well, anybody who goes through the poles at Earth, they have to go through the open areas of the Earth's magnetic shield. And yes, that's right where the radiation storms hit. Those satellites have to be radiation hardened. And a lot of them are. I mean, not all orbits around Earth are the same. They're not all created equal. LEO is not the same as a HEO, is the same as a GEO. And sun-synchronous or polar orbits, or, they're not the same. Space is not space. And so luckily, the savvy contractors and the people who build satellites, if they're smart about it, they know what their radiation specifications are. And they've got good ones. And the ones, you definitely have to have a special kind of electronics, of rad-hard electronics to be able to handle orbits that go through those open regions, especially during solar maximum, as opposed to something that's more in the equatorial plane. Low inclination ones, depending upon how far out they are either in reasonably benign orbits or, they're out in the radiation belts, dwelling in the radiation belts all the time. So it really just depends where you are, and no two orbits are alike. And now we're getting orbits that are these weird ion propulsion orbits that are slow, 5-year, slowly boosted orbits where they have to go through a whole host of different space environments before they even get to their main mission. Those are becoming very challenging for us because it means basically a satellite can't be prepared for just one type of environment, like a LEO environment or a GEO environment. It has to be prepared for the whole gamut because it's going to be spending time in all of these different micro space weather climates. And that's really hard. That's really hard to engineer. So those are some of the new challenges that we're facing. We need to make you a general in the Space Force so you can get money for your weather broadcasting. That's very kind of you. If you know, honestly, if we can get it out in the public eye and we get the public awareness, then the public, I think, can be the grassroots movement and the lobbyists to get a much higher visibility for space weather and get much better coverage and make Congress more responsible for the choices that they make. You know, anything that Congress can shove under the rug, they will. And so right now they're only going to deal with the extreme events. But as the public awareness grows, which is what I'm trying to do, as public awareness of space weather grows and the need for it grows, then Congress will say, well, if it's important to the public, I want to get reelected. And so maybe I need to make it a higher priority for me. So that's kind of the angle I'm going, because a lot of my friends and colleagues have gone the way of policy. And they've hit a lot of dead ends because a lot of the things in space weather are expensive to fix and expensive to address. But if the public wants it and these officials want to get reelected, they're going to listen to their constituents. So I am going straight to you because you are their constituents. And so I'm bypassing, in a sense, I guess I'm bypassing the middleman. I don't know. But that's just the way I'm going about it. Besides, I want you to be able to have the straight poop, you know, and not have it be watered down or, you know, disseminated for you. I want you to be able to see what really is out there and why we need to be concerned about it. So please do a special focus on solar events, of how the solar events affect the ionosphere nature of radio propagation. Yes, that's one that's going to happen. That's going to be later, though. I've got to get through this, and I've got it because my Patreon supporters at the mini course tiers have asked me to do lessons on space weather basics. So I've done, we've done coronal mass ejections, we've done solar flares, we've done radio bursts. I'm now doing solar radiation storms, and then I will do solar wind and high-speed streams. And then I probably will get into the magnetosphere, ionosphere, and talk about these systems. It depends upon what the Patreon members want, what they feel is the most, you know, what is the most popular. And so that is definitely on my list of things to do, but I only do these once a month. And so, you know, we're going to be on solar radiation storms at least for the next couple months. So, but again, all of this is going into the space weather courses I'm doing for Millersville. So just know that, that all this stuff is going to be taught to meteorologists. And so we have to be comprehensive, and it will happen. Could the reason for See Me By houses and buildings were painted back in lead back in the days? I don't think so. I have no idea. That's an interesting question. I don't know the historical reference that you are talking about, so I can't respond intelligently. I think frequent flyer cards are a way of collecting health data based on this. Could be. Yeah. That'd be very interesting if they, you know, a lot more people are carrying these radiation devices though now, if you've noticed, ever since Fukushima. And so people are going up in planes trying to see how the fallout is going, and they get up in the plane and they go, oh my God, I'm getting dosed. This is higher than Fukushima, you know. And they don't realize what they're sensing, the cosmic rays. They're sensing the space weather. You know, if there's a radiation storm, people had no idea when they went up on planes that that there was radiation up there. And so it's been kind of a real awakening for quite a few people who innocently bought these things thinking they were being smart about radiation safety, and then realized, oh my gosh, it's at risk every time I fly. What am I doing? You know, so that's something else that especially as polar routes become more popular with these airlines, that's going to become a bigger deal. And don't even get me started on ADS-B, which is the space-based way of navigating with air traffic control now instead of using ground-based air traffic control operations. ADS-B can be jammed essentially by radiation storms, and that's going to be a problem, but we can get in that some other time. Okay. Yeah, good night, Billy. Thank you for this. I appreciate you staying up so late. I'm sorry that our time zones are so backwards, but thank you for staying up so late. Let's see. Lead paint was for radiation. Yeah, I don't think it had anything to do with radiation storms. Besides, we don't get radiation storms to the ground at Earth. The atmosphere blocks it all. So we didn't even know that we were getting radiation storms for many years. I spoke to an air hostess about this, and she said when they are pregnant, they are allowed to stop flying. Yeah, they're forced to stop flying. A lot of the airline attendants, the flight attendants now, it's sad, but there's a higher incidence of prostate cancer in males, breast cancer in females, and also eye cataracts for pilots, sitting through the front of the plane. There are much higher rates of these types of things, of radiation-borne illnesses in flight attendants than the general population. And some flight attendants know it and some don't. And so this is a problem that we've got to figure out how to stop. In the United States, pilots are considered radiation workers. Did you guys know that? The flight attendants are not. And people say, well, why is that? And I don't really know, but my guess is that it's because the flight attendants share the same cabin as the general populace. And if they were considered radiation workers, then how come the populace isn't? Especially frequent flyers who fly as much as the flight attendants, maybe more. So there are some things that need to be changed, some rules that need to be changed. And also, even in Europe, and I know in Germany in particular, even the pilots are not considered radiation workers. And any radiation plan, in their flight plans, the radiation dose that they calculate is completely optional. So I know a lot of pilots in the EU that are very upset with that and are trying to change that as well. So I'm working with them on some of this stuff. That's only when you fly frequently at high altitude and latitude that there's a risk. Yes and no. It depends. If you fly frequently, sure, but even at mid-latitudes. So if you are curious, you can go to, for instance, in the United States, you can go to radsonaplane.com. That's an outfit that Tony Phillips from spaceweather.com is doing. He's only doing it domestically. I would definitely advertise this stuff more if it were the worldwide, but he's only sticking with domestic flights for the most part, probably because those are the only ones he can fund very easily. But they've been doing radiation dose, testing. They've been taking up a whole bunch of different types of I don't want to say dosimeters, but radiation detectors, and even neutron monitors, and they're checking to see what the radiation doses are in these flights, and even at mid latitudes, the radiation dose it's not non-trivial. It's not outrageous like it is in some of these high latitude flights, but it's more than you'd expect, especially right now at solar minimum. But when you get a solar radiation storm, those things penetrate. Those things can penetrate and cause cosmic ray showers, even at mid latitudes. So we're just beginning to learn a lot more about that stuff, and I'm hoping more studies like his will come online. I'd really like to see more studies like that done at in places like Sweden, in places like Europe. I see it. He's the only one I know that's doing a comprehensive study, at least of the United States. There's also NAIRAS, NAIRAS. That is a radiation modeling thing that was done back in quite a few years ago, where they're looking at what radiation doses will be for for energetic particles in a global model. And they look at the solar wind, they look at the radiation, whether it's galactic cosmic rays or solar radiation, but these radiation storms at the solar wind, and then they run it through a model to get an idea of how deeply the fluxes will penetrate into the upper atmosphere. It was done by Brian Kress and a bunch of colleagues of mine many years ago, and now Kent Tabiska runs it at Space Environment Technologies. You can get an idea of what that is if you go to his website, or you just Google NAIRAS, NAIRAS. But it was funded by NASA many years ago. And so those are some of the more ones that you can access easily through the public eye. There are a few that are behind firewalls and paywalls and stuff like that, but I won't talk about those just because, you know, I don't like the fact that people have to pay for some of this stuff. It's ridiculous. Okay, hopefully that helps for anyone who wants to dig further. What is the cause of the particle acceleration? Well, I went through some of it. You'll see more of it next course. But if you missed it, go back and just re-watch this course when it comes online. Let's see, late 80, early 90s was a huge abatement programs to remove it from public buildings. Oh, you guys are talking about lead again, okay. Okay, so airliners are not going to allow for this. Finnair staff, yeah, good, please do, Amber, please do. And the thing is, I do believe the airlines will allow for this. And the reason why is because they should be able to offer a refundable ticket with space weather insurance. I mean, they stand to make a bundle of money because people who want to be safe, people who are high-risk passengers either getting chemotherapy or radiation therapy, or people who are pregnant, who want to have that peace of mind that, okay, I don't want to get just a refundable ticket for any reason. I want to get just for space weather reasons, so that if I'm ready to fly and I look at the space weather for that day and there's a radiation storm that's about to hit, I can say, nope, 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 I want to reschedule. I don't want to fly during this. And so it's a different cost. It's a different thing altogether than getting a refundable ticket because, you know, of just normal maladies. And so it really could be a potential income server for them. And, you know, they just have to be grandfathered in that anybody, you know, nobody could sue them for, you know, I was on a flight back in 1972 when that fatal, you know, SEP hit, and now I have, you know, colon cancer and it's your fault. You know, stuff like that. That's not going to fly. No pun intended. But I think that there's a real opportunity here to not only make the public safer and arm them with the information that they need, but also for these airline companies and these insurance companies to make, you know, to make it lucrative for them, so that we both get safety and we get, and you know, and they still make a profit. It's not going to just break their backs, which is, you know, everybody wins. That's what you want, is a win-win. So, at any rate, that's what I'm hoping will be the outcome of all this. All right, guys. Well, it looks like my system is freezing again. So, and I think I've answered most of your questions. Let's see. Could radiation for pilots due to more windows be limited protection? You know, man, you're going to have to talk to a composites person, Brian, because there are certain materials that you can use that are radiation safe, and they don't emit a lot of daughter products. But then there are materials that you can use that are very strong, like metals, and if they're certain thickness, they actually can become a source of things like X-rays. So bremsstrahlung can be a problem, for example, and so you could make the radiation dose inside, you know, these flying metal cigars. You can make it worse for the passengers inside than even just the ambient radiation coming in. But that is not, I mean, that's something that needs some heavy engineering to determine. That's not something that's easily determined at all. And I'm not sure how much research is being done on that. However, I will say that with all the land rovers that everybody's trying to make now for the astronauts that are going to be making colonies on the moon, right? They're now trying to do pressurized land rovers so the colonists can you know, travel further away from their campsite, so to speak, and search for water ice at the lunar poles. Those newfangled land rover dune buggy things that they're trying to make, those things are going to be very well researched when it comes to the radiation potential. Because if they're made out of metal, those things will become a source. They'll be, as one of my friends put it, they're like a microwave oven for astronauts. That when a radiation storm comes and the astronauts are stuck inside one of these things, their radiation environment could just absolutely cook them. And so I'm sure there's going to be a lot of research done here very quickly about these types of structures or these types of vehicles. And a lot of that technology will be transferred to the airline industry. Now, it's not as critical for the airline industry, but it's critical enough. So that is kind of where we're going in the future. But that's why we call radiation storms the invisible killer, is because it has exactly that issue, is that we don't see it, therefore we don't know to protect ourselves against it. And that's just the nature of the radiation storms. So yes, this is the invisible killer, and it's a bigger issue than a lot of people would like to admit. But don't worry. Here on the ground, we're fine. In most airline flights, we're fine, especially if they're short. I mean, our bodies are ready. We are Earth creatures. We are used to the environment here at Earth, and a little bit more radiation, is not going to hurt us. But when we go out into space and venture into these other worlds, it's a game changer. So we really do need to pay attention to radiation far more than we are. So, okay, guys, I think that's about it. Yeah, I'm watch the movie The Moon. Yeah, I need to watch. Actually, I want to watch that movie for other reasons too. The psychology of that one. That was also done by Duncan Jones, right? And I think his father was involved in it. So I have multiple reasons to watch that particular movie. If anybody knows, I'm a fan of the Jones family. So okay, guys. Once again, my computer's frozen. My husband probably has the microwave on again. I don't know, but that's all I see of the questions. And if that's it, then I will say goodbye. I've once again almost made it a 3-hour course, even though I didn't mean to. But at least the last, like 40 minutes of it or so has all been questions. So you guys have kept me on for a long time, and I appreciate that. Okay, so I'll say goodbye until next time, and we will pick up where we left off and start talking about how these big radiation storms get to Earth and what they look like when they do. Okay, all right, guys. Talk to you soon. Okay, bye.